Welcome to the Sleepy Cosmos channel, a place where science and serenity meet. Here we explore the quiet wonders of the universe, from dark matter to string theory, all told in a calm, soothing rhythm designed to help you relax, drift, and dream among the stars. Each video is a guided journey through the cosmos, slow, meditative, and filled with real science wrapped in gentle storytelling. So if you love space, curiosity, and the peaceful side of knowledge, you're in the right place. Make sure to subscribe for more new sleep narrations every week. And if you'd like to reach out for collaborations or business inquiries, you can contact us at the sleepycosmoschannel@gmail.com. Now, settle in, take a deep breath, and let's drift into the universe together. Welcome, wherever you are listening from, however your day has unfolded. You are here now, resting, breathing, letting your attention drift upward toward the quiet sky and beyond. Tonight, we will allow the mind to wander far out into the universe and far forward in time. We will look gently, carefully at what science tells us about the very distant future, at the fate of stars, the cooling of space, and the slow, steady rise of entropy, all spoken softly, calmly, like a scientific lullaby. This is not a story of fear and not a story of drama. It is a story of natural processes, unfolding across unimaginable spans of time. And as we follow these ideas, we do so with quiet curiosity and with a sense of calm, breathing in and breathing out, letting the rhythm of the universe match the rhythm of your breath. When we study the cosmos, we are really studying change. Every star you have ever seen, every galaxy, every atom exists in motion. Heat flows, energy spreads, structures form, and then slowly dissolve. And underneath it all, guiding the direction of time, is entropy. Entropy is the simple and deeply powerful idea that systems tend to move from ordered states into more disordered ones. Heat spreads, gas expands, energy becomes less concentrated and less available to do work. In our daily lives, we notice the small expressions of this law. A hot drink grows cool, never suddenly becoming hot again. A carefully arranged room slowly drifts toward mess, unless energy is added to restore order. Ice melts, glass shatters, and smoke disperses through the air. Each of these is a quiet whisper of the second law of thermodynamics, the law that tells us that entropy tends to increase. And this same law applies not only to cups of tea or scattered papers, but to the universe itself, to the gas between stars, to the radiation drifting through space, to the very structure of galaxies. Everything moves, slowly, towards states where energy is more evenly spread out, where temperature differences fade, where the ability to create change grows weaker. This tendency is what we call the arrow of time. It is why the past feels fixed and the future feels open. It is why we remember what has already happened, but cannot yet recall what is to come. Entropy increases and time flows forward, quietly, steadily, and the universe follows this flow. Cosmologists, the scientists who study the universe as a whole, use both observation and theory to understand how this process unfolds on the largest possible scales. They study the light from distant galaxies, the faint glow of the cosmic microwave background, and the motions of clusters of stars. They build models, test them, refine them, and slowly, a picture emerges. It is a picture of a universe that began, hot, dense, and filled with radiation, a universe that expanded, cooled, and formed atoms, then stars, then galaxies, a universe that continues to expand today, its fabric stretching, its structures drifting apart. And as the universe expands, it cools. Radiation spreads out, wavelengths stretch, and the average temperature of space drops ever closer to absolute zero. Not today, not tomorrow, but over timescales so vast that human language can barely hold them. Millions of years. Billions of years, trillions of years, time so deep that even the idea of memory dissolves. And still, entropy rises slowly, inevitably, like the faintest tide crossing an infinite shore. This idea that the universe may one day reach a state of near-perfect uniformity, where energy is spread so thinly and so evenly that nothing more of interest can happen, is called the heat death of the universe. The phrase can sound dramatic, even frightening, but in truth, it is not a violent ending. It is not an explosion or a collapse. It is a gradual fading, a quiet, almost imperceptible softening of contrast. As differences in temperature, pressure, and energy slowly decline, until, eventually, there is nothing left to drive change. The universe would not vanish. it would simply rest, in a state very close to thermal equilibrium, where entropy is near its maximum possible value, and the arrow of time, as we understand it, would lose its meaning, because there would be no further large-scale change to mark the passing of moments. And yet, even in contemplating such an ending, we are reminded of something profound, that the universe, for all its cold laws and strict regularities, is also a place of astonishing beauty. From the birth of stars to the formation of planets to the rise of life, complexity blooms for a while. Structures form, grow, shine, and then gently pass away. Not because the universe is hostile, but because change is fundamental. Because energy, once concentrated, will eventually disperse, and entropy will continue to rise. As you listen, you may begin to feel how small our human timescales really are. A single lifetime, a century, a civilization, all are brief sparks set against a cosmic background of trillions of years. And yet this does not make our lives meaningless. If anything, it shows us how precious each moment truly is. A rare arrangement of atoms, briefly holding together, to think, to feel, to wonder, before dissolving back into the wider universe. In this way, we are not separate from the cosmos. We are expressions of it. Temporary patterns, formed by the same physical laws that guide stars and galaxies. We are the universe, momentarily aware of itself, breathing, thinking, listening. Science allows us to trace this story, not as myth, but as a careful reconstruction based on evidence. Telescopes peer back in time to when the universe was young. Satellites measure the faint afterglow of its birth. Theories, rooted in mathematics and experiment, reveal how energy and matter behave. And from all of this, a consistent narrative emerges, a universe that began hot, dense, and simple, that grew, expanded, and cooled, that formed complexity, structure, and even life, and that will one day, far beyond any time we can personally witness, settle into a cold, dark, and almost perfectly uniform state, the final expression of rising entropy. As we journey through these ideas together, there is no need to rush. Each thought can arrive slowly, rest for a while, and then drift on. Just as galaxies drift apart across expanding space, just as light travels calmly through the dark. Tonight, you are invited to relax into this perspective, to let everyday concerns grow quieter, smaller, simpler, and to rest in the vastness of cosmic time, knowing that you, just like every star, every atom, every grain of dust, are part of this grand, slow, and beautiful unfolding. For now, feel the breath, feel the body at rest, and allow the steady, gentle rhythm of the universe to carry you onward into quiet curiosity and deep, peaceful wonder. Imagine for a moment that everything you know, every person, every object, every memory, is part of a larger stage, a stage so vast that it contains all stars, all galaxies, all the empty space between them. This stage is the universe. And to understand where the universe is going, we first need to understand what this stage is made of, how it bends, how it changes, and how time itself flows within it. When physicists talk about space, they are not referring to a simple featureless void. Space is not just an empty box in which things sit. It is a dynamic, flexible structure, a fabric that can stretch, curve, and ripple. This idea arises from general relativity, the theory that describes gravity, not as a force pulling objects together in the old sense, but as the curvature of space and time, caused by the presence of mass and energy. A massive object, like a star or a planet, changes the geometry of the space around it. Other objects, and even light, follow the curved paths defined by that geometry. To us, this appears as gravitational attraction. So the stage is not rigid, it responds to what is on it. It changes as matter and energy move. Time is intimately linked to this stage. In everyday life, we picture time as a separate thing, a universal clock, ticking the same way everywhere. But in the physics of the universe, space and time form a single, interwoven structure. We call this structure space-time. Events happen at particular locations in space and at particular moments in time. These coordinates can be combined into a four-dimensional description, 3 dimensions for space, 1 dimension for time. The geometry of this four-dimensional structure is shaped by energy and mass, and in return, that geometry tells matter and light how to move. This deep connection between space, time, and energy is one of the most important pieces of the cosmic puzzle, because it means that the overall shape and evolution of the universe depend on what the universe contains. So what does the universe contain? On the most familiar level, it contains atoms. Atoms are tiny systems, with a dense nucleus made of protons and neutrons, surrounded by a cloud of electrons. These atoms combine to form molecules. Molecules build up into the matter we see around us: rock, gas, water, living tissue. This ordinary matter is called baryonic matter, a term that refers to particles like protons and neutrons. It interacts with light. It can emit light, absorb it, and scatter it. Because of this, we can see it directly with telescopes. But ordinary matter is only a small fraction of the universe's total content. Observations of galaxy motions, of gravitational lensing, and of the cosmic microwave background all tell us that there is more gravity than ordinary matter can account for. Galaxies rotate too quickly to be held together by visible matter alone. Clusters of galaxies bend light more strongly than visible matter would allow. The detailed patterns in the ancient light from the early universe also reveal a surplus of mass. The simplest explanation is that there exists another form of matter, non-luminous, not interacting with light in the familiar way, but still responding to gravity. We call this dark matter. It does not glow, it does not absorb or emit, yet its gravitational influence helps shape galaxies, forms halos around them, and contributes significantly to the overall density of the universe. There is another, even stranger component. When we observe distant supernova and measure how quickly the universe is expanding, we find that the expansion is not slowing down, it is accelerating, as if space itself is being gently pushed apart. This effect cannot be explained by matter alone. Instead, it suggests the presence of something with a kind of negative pressure, a component of the universe that acts uniformly everywhere. Driving accelerated expansion, we call this dark energy. Its precise nature is still unknown. It may be a property of empty space itself, a constant energy density that does not dilute as the universe expands, or it may be something more complex. What we do know from multiple independent observations is that dark energy contributes the majority of the total energy content. Dark matter adds a large share. Ordinary matter, the stuff of stars and planets and people, makes up only a small slice. So the cosmic stage is not just a vacuum sprinkled with familiar objects. It is a blend of ordinary matter, dark matter, radiation, and dark energy, all interacting through gravity and all influencing the shape and fate of space-time. Now, we step back and look at this stage on the largest scales. When astronomers map galaxies, they see that on average, galaxies are receding from one another. The farther away a galaxy is, the faster it appears to be moving away. This relationship between distance and recession speed is one of the foundational observations of modern cosmology. It is not that galaxies are flying through space like projectiles. It is that space itself is expanding. You can picture this with a simple analogy. Imagine points drawn on the surface of a balloon. As the balloon is inflated, the distance between any two points increases, even though the points themselves are not moving across the surface. In a similar way, as the universe expands, the distance between galaxies on large scales increases. This expansion was faster in the past, then slowed under the influence of gravity, and more recently began to accelerate due to dark energy. This dynamic behavior, expansion, slowing, and acceleration, is built into our best models of the universe, and it has profound consequences. Because as space expands, radiation stretches, light waves become longer, their energy decreases, the overall density of matter and radiation drops, everything becomes more dilute, the universe cools. From a thermodynamic point of view, expansion changes the conditions under which entropy grows. In a simple, closed system of fixed volume, entropy tends toward a maximum value. In an expanding universe, the total possible entropy can increase over time, because there is more space, more degrees of freedom, more ways for energy and matter to be arranged. At the same time, local processes, such as star formation, galaxy mergers, and black hole growth, change how entropy is distributed. The universe is not just expanding, it is evolving, passing through phases, each with its own characteristic structures, and each altering the balance between order and disorder, between concentrated energy and diffuse, unavailable energy. To see this more clearly, consider entropy again from a more intuitive angle. Entropy can be connected to probability. A highly ordered state, like gas confined to half of a box, is relatively unlikely. There are fewer microscopic arrangements that keep all the gas molecules on one side. If you remove the barrier, the gas spreads, soon it fills the whole box. This full box state can be realized in an enormous number of microscopic ways. The system spends almost all of its time in that kind of configuration. That is why we associate it with higher entropy. The key is that the system naturally moves from less probable macroscopic states to more probable ones. Now scale up this reasoning, replace the gas in a box with matter and radiation in an expanding universe. Early on, the universe was hot, dense, and relatively uniform. As it expanded and cooled, small fluctuations in density grew under gravity, forming galaxies and clusters. In a sense, these structures look like order, clumps in an otherwise smoother background. But at the same time, the processes that form them release energy, heat surrounding gas, emit radiation. These all contribute to an overall increase in entropy. Black holes, in particular, carry enormous entropy proportional to the area of their horizons. When matter falls into them, the entropy of the universe rises dramatically. So what appears as order on one level is accompanied by increased disorder on another. Gravity and thermodynamics are intertwined. The universe forms islands of structure, while the global total of entropy moves upward. Within this evolving background, we can distinguish regions where order and activity are still strong, and regions where entropy is already high. Dense, cool objects like stellar remnants and diffuse radiation spread across vast volumes of space. As time goes on, the balance shifts, more matter ends up, locked in compact remnants, more energy is radiated away, more black holes grow, and later, much later, begin to evaporate. Each step transfers energy from concentrated forms into wider, more uniform distributions, towards states where temperature differences have largely vanished, where there are very few gradients left to drive change. If we zoom in on a smaller scale, we see a tension between order and chaos. Stars, galaxies, and planetary systems are not permanent. They are transient structures, maintained only as long as certain conditions hold. A star exists because inward gravity is balanced by outward pressure, generated by nuclear fusion in its core. When the fuel runs out, that balance fails. The star either contracts into a dense remnant or explodes and disperses its outer layers. The materials forged in its core are released to be incorporated into new systems. Each such event is both an ending and a beginning. On a larger scale, galaxies interact, they merge and collide. Tidal forces distort their shapes. Gas clouds are compressed, triggering new star formation. Later, gas is used up or expelled. Star formation slows. The galaxy gradually turns from a bright, active system into a dimmer collection of long-lived stars and remnants. All of this is happening against the backdrop of expanding space, in which galaxies that are not gravitationally bound to each other drift farther and farther apart. Over extremely long times, most galaxies will recede beyond each other's horizons, unable to interact or exchange light. The universe becomes more fragmented, each island of matter surrounded by enormous regions of near-empty space. This interplay between local order and global drift toward randomness is one of the central themes of cosmic evolution. Gravity can create pockets of structure in an overall expanding, entropy-increasing universe. But even these pockets are temporary. Over enough time, their energy gradients fade, their matter disperses or collapses into remnants, and the remnants interact less and less as the distances between them grow. Impermanence is not just a poetic idea, it is a physical result of how space, time, matter, and entropy work together. You can feel, in this description, a certain quiet rhythm. On the one hand, there is the stability of physical law, the equations that govern space-time, the rules of thermodynamics, the behavior of matter and radiation. On the other hand, there is the flow, the fact that these rules do not freeze the universe in place, they drive it forward, from simplicity to complexity, and then gradually toward a different kind of simplicity, from a hot, dense, young universe to a richly structured, middle-aged cosmos, to a much older state with few active processes and high entropy. We, as observers, happen to exist during a window when complexity is abundant, stars shine, planets remain warm enough for chemistry, energy gradients can sustain life, but this window is framed by the deeper tendency of entropy to rise and of energy to spread. As you rest with these ideas, notice how they connect. Space is the stage, time is the measure of change, matter and energy shape the stage and respond to it. the universe expands, radiation stretches and cools, entropy increases, gravity sculpts structures that eventually grow quiet. Order and chaos are not opposites locked in battle. They are different aspects of the same physical narrative, seen at different scales and at different moments. In this narrative, everything changes, but the rules stay the same. And through those rules, we can begin to understand how a universe that is vibrant and structured today may slowly, ever so slowly, drift toward a state where almost nothing of that structure remains. To feel how these abstract ideas connect to daily life, it can help to return for a moment to simple, familiar scenes. Imagine holding a hot mug of tea. At first, the mug feels warm in your hands, steam curls upward. If you place the mug on a table and simply wait, heat flows from the hotter tea into the cooler surrounding air. Gradually, the temperature of the tea and the temperature of the room move closer together. After a while, the tea is lukewarm. Even later, it reaches room temperature. There is no longer a useful temperature difference. You cannot run an engine from room temperature tea and room temperature air. The ability to do work has been lost, not because energy vanished. The total energy of the tea plus the room is essentially the same, but that energy is now spread out more evenly. Its entropy is higher, and so its capacity to cause change has diminished. Or think of an ice cube placed in a glass of warm water. At first, the ice is very cold. The water is warmer. Heat flows into the ice melts, becoming liquid water. Over time, all of the water reaches a uniform temperature. Again, the temperature differences that drove change have faded. Energy has been redistributed. Entropy has increased. The process will not spontaneously reverse. You will not see room temperature water separate itself, forming a colder solid cube and warmer liquid. The laws of physics would allow such a configuration, but it is fantastically improbable. There are far more ways for the molecules to be arranged in a uniform higher entropy state, so that is where the system goes. Now stretch your imagination. Replace the room with a galaxy. Replace the mug with a cluster of stars. Replace the glass of water with a region of hot gas. The details are different, but the core idea is the same. Energy flows, differences in temperature and density, drive change. Radiation carries energy away, gas clouds cool and contract, stars form, shine, and eventually die. Each stage redistributes energy, each event nudges the universe. Further along, the path from low entropy to high entropy, from strong contrasts to more uniformity, from readily usable energy to energy that is diffuse and inert. The universe itself can be imagined as a vast, ever-widening ocean. In the earliest times, this ocean was hot and dense. Its waves were short, its contents tightly packed. As cosmic expansion proceeds, the ocean gently widens. The same amount of energy is spread across an ever larger volume, like waves that stretch and lengthen. Radiation is redshifted, its wavelength grows, its energy per photon drops. The average temperature of the cosmic ocean falls. What was once a blindingly bright, high-energy environment becomes over billions of years a cooler, more transparent, and more spacious sea. Within this sea, islands form, galaxies, clusters, filaments of matter. These are like archipelagos, temporary features, created by the interplay of gravity, motion, and the initial distribution of matter. But the ocean continues to widen. The islands drift apart. Currents gradually weaken. Over an immense timescale, the structures that now define the universe become more isolated and eventually more eroded, until even these islands are worn down by the slow, relentless rise of entropy. This image of an ever-enlarging cosmic ocean is not just poetic, it encodes specific physics. The metric that describes the geometry of the universe includes a scale factor, a number that tells us how big the universe is relative to some reference time. As this scale factor grows, distances between unbound objects grow, the density of matter drops, the temperature associated with background radiation falls. When we say the universe expands, we are saying that this scale factor increases, turning a compact, hot, early cosmos into the large, cool, structured, and eventually thinned-out cosmos we infer today. Within this grand story, it is helpful to highlight once more the role of the arrow of time. From the standpoint of fundamental laws at the microscopic level, many processes can be reversed. The equations that describe particle interactions often work equally well if we replace forward in time with backward in time. Yet our experience is not symmetrical. We remember yesterday, we do not remember tomorrow. We see eggs breaking, we do not see broken eggs reassembling. We observe gases spreading, not spontaneously compressing. This asymmetry between our memories and our expectations, between what we see happening and what we never see happening, is rooted in entropy. The universe began in a state of very low entropy compared to what is possible. As time passes, systems move toward more probable, higher entropy configurations. This provides a direction, an arrow, from past to future, from lower entropy to higher, from a universe in which many complex processes are still possible to a universe in which fewer and fewer remain. Once you see this pattern, you can recognize it. In many aspects of daily life, a tidy room left unattended tends to become cluttered. Papers spread out, dust accumulates. Order requires energy, it requires effort. A person must come in and rearrange things, use energy stored in food, ultimately derived from the sun, to locally reduce entropy, but that reduction is more than compensated by the increase in entropy associated with the person's metabolism and with the production of waste heat. Local order, global disorder rising. A phone battery has energy stored in a way that can do useful work, powering a screen or a processor. As the battery discharges, energy is transformed into light, motion, and heat. Eventually, the stored energy becomes more uniformly spread. At that point, the battery can no longer do work. It has moved closer to thermodynamic equilibrium. Again, nothing mysterious, just the same story of concentrated energy being used and then relaxing toward a more disordered state. The universe is this logic writ large. Every star is a battery, a region where nuclear fuel is converted over time into radiation and into heavier elements. The star shines because there is a gradient between its hot core and the colder space around it. This gradient allows energy to flow outward, doing work, heating gas, driving winds, illuminating planets. When the fuel is exhausted, the gradients weaken. The star, in whatever remnant form it takes, cools. It emits its remaining heat into an ever colder universe, moving toward equilibrium. Galaxies, too, are maintained by flows of energy from supernova, from active black holes, from ongoing star formation. These processes stir gas, counteract gravitational collapse, shape the interstellar medium, but all of them consume free energy. They accelerate the rise of entropy. They draw down the universe's store of easily usable gradients. What appears as vivid, bright, and dynamic is part of the mechanism by which the cosmos approaches a quieter, higher entropy state. In human experience, impermanence is often felt as a source of anxiety. We age. Relationships change, societies evolve, bodies weaken, memories fade. But when you widen the lens, impermanence appears as a universal property. It is not targeting you. It applies equally to stars, to galaxies, to black holes, to clusters, to any structure that depends on gradients and flows over long enough timescales. All such structures are transient. This is not because there is something wrong. It is because the underlying laws drive systems toward configurations in which gradients are minimal, in which entropy is high, in which chance fluctuations still occur, but large-scale organized processes are rare and weak. When we say that the universe may end in heat death, we are taking this logic to its farthest implication. If expansion continues, if entropy keeps increasing, if no new physics intervenes, then eventually there will be so little free energy, so little contrast, that almost nothing of the complexity we now see will remain. All that will be left is a thin, cold, mostly uniform distribution of very low energy particles and extremely long wavelength radiation, perhaps with rare tiny fluctuations, against an almost unchanging background. This destination can seem somber, but it is also remarkably orderly. It is the endpoint of a process that began with a hot, dense, low-entropy early universe and passed through a phase of stars, planets, life, and consciousness. In this sense, the current era is like a narrow band between two extremes. One extreme is the simplicity of the early hot plasma. The other is the simplicity of the late cold equilibrium. Between them lies complexity. We exist in that band right now. Understanding this gives us a firm conceptual frame for the idea of heat death. The universe is a dynamic stage, space and time interwoven and shaped by energy. Matter and energy exist in multiple forms: ordinary matter, dark matter, radiation, dark energy. The universe expands like an ever-widening ocean, stretching radiation, cooling the background. Entropy increases, turning gradients into uniformity, forming and dissolving structures. Stars, galaxies, black holes, all are temporary islands in a sea that is ultimately moving toward equilibrium. With this frame in place, we can now look more deeply at entropy itself and at the arrow of time that arises from its steady, quiet climb. Entropy is one of the most important ideas in all of physics, and at the same time, it is one of the most misunderstood. People often hear the word and think simply of disorder or chaos, a messy room, a broken glass, a system that has gone from neat to disorganized. There is some truth in that picture, but underneath is a more precise and deeper meaning, one that links heat, probability, information, and the flow of time itself. The story of entropy begins with the study of heat engines. In the 19th century, physicists and engineers were trying to understand how efficiently machines could turn heat into useful work. They noticed that no engine could convert all of its heat input into mechanical output. Some energy was always lost as waste heat. This was not just a limitation of engineering skill, it was a fundamental limit. From this realization, the laws of thermodynamics were developed. The first law expresses conservation of energy. Energy cannot be created or destroyed, only transformed. The second law introduces entropy. It tells us that in any natural process where energy is transformed, the total entropy of a closed system will not decrease. It can stay the same in idealized reversible processes, but in real processes, it increases. This increase is what makes certain processes irreversible. Heat flows from hot to cold. Engines always produce waste. Broken glasses do not spontaneously reassemble. The second law captures all of these observations in a single mathematically precise statement. Later, a new perspective emerged. Physicists began to connect the macroscopic description of thermodynamics with a microscopic description in terms of atoms and molecules. A gas in a box can be described macroscopically by its pressure, temperature, and volume, but microscopically it consists of a huge number of molecules, each with its own position and velocity. A macrostate is a description of the system in terms of a few bulk quantities like pressure and temperature. A microstate is one particular detailed arrangement of all the molecules at a given macrostate. There can be many microstates, many precise ways for the molecules to be arranged that all correspond to the same macroscopic values. Entropy measures how many microstates are compatible with the macrostate. The more microstates, the higher the entropy. This view explains why high entropy states are so likely and low entropy states are so rare. Suppose you have a box divided into two equal halves. All the gas molecules are initially confined to the left side. The macrostate is all gas on the left. The number of microstates compatible with this condition is large, but if you remove the barrier, the gas molecules are free. They spread out. Soon, half the molecules will be on the left, half on the right. The macrostate becomes gas evenly spread. The number of microstates that look like this is vastly larger than the number that look like all gas on one side. The system naturally moves from the less probable macrostate to the more probable one, from low entropy to high entropy. Not because there is a preference built into the universe, but because random motion will almost always push the system into regions of phase space where there are more microstates. It would be technically allowed for the gas to spontaneously flow back into the left half, but that would require a highly coordinated motion of an enormous number of molecules. The probability of that happening is so small that we effectively never see it. This is why entropy tends to increase and why we observe a direction to processes, even when the underlying microscopic laws are symmetric in time. This statistical understanding bridges the gap between microscopic reversibility and macroscopic irreversibility. At the level of individual particles, the equations can usually run forward or backward, but when we look at large collections, we see an overwhelming bias toward higher entropy states. This bias is what defines the arrow of time. The direction we call future is the direction in which entropy increases. Heat and work are two different ways that energy can move. Heat is energy transfer. Due to temperature difference, it is disordered. Microscopic motion, molecules moving faster, vibrations becoming more intense. Work is energy transfer that can be fully organized. Lifting a weight, compressing a gas, driving an electric current. When energy is concentrated in an organized form, it can be used to perform work. But as processes unfold, some of that organized energy is degraded into heat, into disordered motion that is more difficult to harness. For further organized change, the second law puts a limit on how much work can be extracted from a given amount of energy, given the temperatures of the heat reservoirs. There will always be some entropy increase, some energy that becomes unavailable. For doing work in the universe, this means that over time, the store of free energy, energy available to do work, is drawn down. It is not that energy disappears, energy is conserved, but more and more of it ends up in forms that are spread out at nearly uniform temperatures. Forms that are poor for driving new processes. This is central to understanding heat death. It is not the absence of energy, it is the absence of useful gradients, the absence of differences that can fuel engines, that can power life, that can sustain change. Now consider the connection between entropy and our psychological sense of time. We remember events in one direction, we recall the past, not the future. Why, on a fundamental level, our brains are physical systems. They store information by creating correlations between their internal states and the external world. When you form a memory, your brain moves from a relatively low entropy configuration to a higher entropy one. You imprint patterns, synaptic strengths change, metabolic processes release heat. Overall, entropy increases. The physical act of remembering requires an increase in entropy. This process happens in the direction where entropy is rising, so memories accumulate. In that direction, which we label forward in time, the past is the direction in which entropy was lower. The future is the direction in which entropy is higher. Thus, the arrow of time is not just an abstract concept. It is tied to how information and memory work in the brain, to how records form and persist. Carbon rings in tree trunks, sediment layers in rocks, light from distant galaxies, all of these are records of lower entropy states that evolved into higher entropy ones. The direction in which those records accumulate defines the temporal arrow. Entropy also connects to information. In a quantitative way, in information theory, we can measure the uncertainty associated with a set of possible messages or outcomes. This measure has the same mathematical form as thermodynamic entropy. The more uncertain we are, the higher the information entropy. In physics, the more microstates compatible with our macrostate, the higher the thermodynamic entropy. These are not identical concepts, but they are deeply related. Both express a kind of spread, a measure of how many possibilities are in play. This connection suggests that entropy is not only about physical disorder, it is also about knowledge. When we know very little about the detailed state of a system, we describe it with a high entropy. When we know more, we describe it with a lower entropy. In cosmology, we often describe the state of the universe statistically because we cannot know the precise microstate of every particle. Entropy becomes a way to encode our coarse-grained description of what is physically present and how it can evolve. In everyday life, we see entropy in the tendency of mess to grow. A tidy workspace left alone tends to accumulate clutter. It is not that there is a force actively pushing things into disorder. It is that there are many more ways for objects to be scattered than to be neatly arranged without sustained effort and sustained input of energy. The more probable configurations will dominate. In the kitchen, clean dishes, dry and stacked, represent a low entropy state. There are fewer arrangements that keep them perfectly orderly. As time passes, we use them, move them, mix them with other objects. Entropy increases. To restore order, we must again spend energy scrubbing, heating water, running appliances. Every act of cleaning is a local decrease in entropy, paid for by an overall increase in the combined system of home and environment. The same is true of biological systems. A living cell maintains a highly organized internal structure, concentrations of ions, carefully folded proteins, complex molecular machines. To maintain this order, the cell must constantly take in nutrients, convert chemical energy, export waste and heat, increase entropy outside. To sustain low entropy inside, life is not a violation of the second law, it is an expression of it, a flow, where order is maintained locally at the cost of greater disorder globally. When we lift our gaze from kitchens and cells to the universe at large, we find similar patterns. Where does entropy live? On cosmic scales, it resides in many places, in the thermal radiation, filling space, in the random motions of gas between galaxies, in the internal states. of stars and remnants, and most dramatically, in black holes, radiation that permeates the universe carries entropy because it can be arranged in many microscopic patterns. Even a faint bath of low-energy photons represents a large number of possible quantum states. Gas, spread through intergalactic space, has entropy tied to the ways its particles can be distributed over positions and velocities. Black holes have entropy associated with the area of their event horizons. An area measured in Planck units, each tiny patch of horizon can be thought of as holding a bit of information about the states hidden within. When matter falls into a black hole, the black hole's area grows, its entropy increases. This process allows the universe's total entropy to rise enormously. Black holes act as vast reservoirs of entropy, collecting and concentrating, the disorder produced by countless processes throughout cosmic history. All of this is happening. In an expanding universe, expansion changes how energy is diluted and how entropy is distributed. As space grows, radiation is redshifted, its energy density decreases, but the number of available states for that radiation increases. Massive particles move farther apart. Gravitationally bound regions remain cohesive locally, but drift away from other regions globally. The question of how entropy behaves in an ever-expanding universe is subtle. Locally, entropy increases. As stars burn, as structures form and evolve, globally, the maximum possible entropy also increases. Because there is more space, more room for radiation and particles, more potential horizon area for black holes over exceedingly long times, as matter decays or is consumed by black holes, and as black holes themselves very slowly evaporate, energy is converted into lower and lower temperatures, into longer and longer wavelength radiation, into distributions that are more uniform. Across the accessible space, the universe moves toward a state in which entropy is near maximal, where matter and energy are spread as evenly as possible. Given the constraints of the cosmic dynamics, this is what is meant by approaching thermal equilibrium. On the largest scale, a state where there are no significant gradients to exploit, no easy ways to extract free energy and build or maintain complex structures in that distant future. Entropy has not just increased, it has nearly saturated within the limits allowed by the universe's size and contents. Processes that once drove change will have largely run their course. Stars will no longer form. Matter will be locked in low-energy remnants or dissolved into radiation. Black holes will have released their stored energy as faint, cold radiation. The universe will be filled with particles and photons, spread thinly at a temperature very close to absolute zero. This is the thermodynamic endpoint, toward which the arrow of time is pointing, not in our lifetimes, not in any time frame. That concerns daily life, but as the long-term limit of the same principles that govern melting ice, cooling tea, a cluttered room, a living cell, a shining star. Through entropy, these diverse phenomena are connected. The quiet increase of microscopic possibilities, the steady erosion of gradients, the emergence of an arrow of time ties together thermodynamics, statistical mechanics, information theory, and cosmology. And it is this same framework that will allow us to understand not only why time seems to flow, but how the expanding universe moves from a bright, active past through the present era and eventually into the deep, subtle equilibrium we call heat death. Imagine looking up at the night sky. You see points of light that seem fixed on a dark dome. For most of human history, it was natural to assume that the universe beyond Earth was static, that stars were embedded in a celestial sphere, perhaps rotating, but not expanding, not evolving, just enduring. It is only within the last century or so that we have discovered the universe is not a quiet, unchanging backdrop. It is dynamic, and on the largest scales, it is stretching. When astronomers observe galaxies, they can measure how light from these galaxies is shifted compared to the light we would expect. Many galaxies show a shift toward longer wavelengths, a reddening. This effect is called redshift. Part of it can be understood in terms of motion. When a source of waves moves away from you, the waves you receive are stretched, their frequency decreases. This is true for sound waves, and it is true for light. If a galaxy is moving away, its light appears redshifted. But when we map many galaxies, we find something more. The amount of redshift is roughly proportional to the galaxy's distance. The farther away a galaxy is, the larger the redshift. On average, This pattern is not what we would see if galaxies were just flying through a static space in random directions. Instead, the simplest explanation is that space itself is expanding. The distance between galaxies that are not bound together by gravity grows over time. Each galaxy is mostly at rest in its local region, but the fabric between them is stretching so that, from any given galaxy's point of view, distant galaxies seem to be receding. The same way, from every vantage point, to get an intuition, we can return to a familiar analogy. Imagine a flat sheet of rubber. On the surface, you draw small dots to represent galaxies. Now slowly stretch the sheet. You will see the distances between the dots increase. Dots that start farther apart end up moving away faster, because there is more rubber between them to stretch. None of the dots has a privileged central position. The expansion looks the same from any dot's perspective. Similarly, in our universe, there is no special center from which everything is flying away. On large scales, every location can be treated as if it were central, because the expansion is happening everywhere. Space is not expanding into something else. It is simply changing its scale internally. This cosmic expansion was first inferred from observations of galaxies in the early 20th century. Later, it became a cornerstone of the standard model of cosmology, a model in which the universe began from a hot, dense state and has been expanding and cooling ever since. At first, this expansion was rapid. Then gravity, due to matter and radiation, slowed it down. One might have expected that as time went on, the expansion would continue to decelerate, perhaps even reverse, if the density were high enough. But when astronomers measured distant supernovae as standard candles, they found something surprising. The expansion is not simply slowing, it is accelerating, as if some unknown component is pushing space to expand more rapidly. This is what we call dark energy. Dark energy behaves very differently from ordinary matter or radiation. Ordinary matter dilutes as the universe expands. Radiation dilutes and also loses energy as its wavelength stretches. But dark energy, at least in the simplest models, does not dilute. In the same way, if it is a property of empty space itself, then as space expands, there is more space, and with it, more dark energy. The density of dark energy remains roughly constant, even as the volume grows. The effect on the dynamics of expansion is subtle at first. When the universe was young, matter and radiation were more concentrated. Their gravity dominated, slowing the expansion over time as matter spread out, and radiation cooled. Their influence weakened. Dark energy became dominant, turning gradual deceleration into acceleration. In this regime, structures that are not already bound will find it harder to come together and easier to drift apart on large scales. The universe becomes increasingly dominated by this accelerating expansion. To appreciate the scale of the universe and how expansion shapes it, it helps to step through its hierarchy of distances. On the scale of planets and stars, space does not expand in any noticeable way. Gravity and other forces hold systems together. Your body, a house, the Earth, the solar system, all are far more strongly bound than any effect due to expansion. On the scale of galaxies, gravity also dominates. Stars orbit within galactic disks held by the galaxy's mass. Expansion does not directly tear apart a galaxy within clusters of galaxies. Gravity, again, can overcome expansion. Galaxies within a cluster orbit their common center and remain gravitationally linked. But on scales larger than these bound structures, expansion matters. Clusters, superclusters, filaments of galaxies with great voids between them, all participate in the general expansion. The distances between these large structures increase over time. Now consider the numbers. The distance from Earth to the Sun is about 1 astronomical unit. Light takes a bit more than 8 minutes. To travel it, the distance to the nearest star is measured in light years. Light years are the distance light travels in 1 year. Our Milky Way galaxy is on the order of 100,000 light years across. The distance to the Andromeda galaxy is about a few million light years. The distance to the most remote galaxies we can observe is on the order of tens of billions of light years. Because space has expanded, while the light was traveling, these scales are enormous, and yet the same rules apply. Where gravity holds, structures stay together. Where it does not, expansion dominates and adds ever more distance between island universes. Cosmic expansion is intimately linked to the universe's temperature. In its early stages, the universe was filled with a hot plasma. Particles and radiation were tightly coupled. As space expanded, this plasma cooled. Eventually, the universe cooled enough for electrons and protons to combine into neutral atoms. At that moment, radiation decoupled from matter. Light could travel freely. This ancient light has been traveling ever since, stretched by cosmic expansion. Its wavelength lengthened, its energy reduced. Today, we detect this radiation as the cosmic microwave background, a nearly uniform bath of microwave photons filling all of space. Its temperature is just a few degrees above absolute zero. Absolute zero is the temperature at which particles would have minimal motion. The cosmic microwave background represents the cooled remnant of the once raging thermal energy of the early universe. As the universe continues to expand, this background will cool further. Its photons will stretch to longer wavelengths, their energy becoming even smaller. The effective temperature of this radiation will gradually sink toward zero. This cooling is not limited to the background radiation. When galaxies emit light, that light is also stretched as it travels through expanding space. By the time it reaches a distant observer, its wavelength is longer, its frequency lower. This process is also described as redshift over very long timescales. The cumulative effect is that more and more energy is stored in very low-frequency, long-wavelength photons. These photons interact weakly with matter. They are hard to detect. They contribute to a background that becomes smoother and colder with time. The universe not only thins, it also dims. On human timescales, the night sky appears unchanging, but if we could see across billions and trillions of years, we would witness profound transformations. Distant galaxies that we can now observe will eventually redshift so strongly that their light becomes undetectable. They will cross a kind of cosmic horizon, beyond which information from them can no longer reach us. Even in principle, only the galaxies that are gravitationally bound into our local group will remain in mutual contact far in the future. An observer living in such a galaxy group might see only a single large galaxy formed from mergers, surrounded by darkness with no clear evidence of the wider cosmic web that we infer today. The universe will appear smaller to those observers, not because it has shrunk, but because expansion has carried most structures beyond their observable horizon. The deep sky will transition from a rich tapestry to a sparse and eventually nearly empty scene. Over unimaginably long times, stars will exhaust their fuel. Bright blue stars live short lives, on the order of millions of years. Fainter red stars can live for trillions of years, much longer than the current age of the universe. Eventually, even these long-lived stars will burn through their hydrogen, leaving behind white dwarfs, neutron stars, and perhaps black holes. White dwarfs will slowly cool, radiating away their residual heat over vast intervals. They will fade into cold, dark objects, sometimes called black dwarfs. Neutron stars will also cool, becoming ever dimmer. Some may collide or be consumed by black holes. Black holes will dominate as massive, compact objects, gradually accreting whatever matter remains in their vicinity. While all of this unfolds, the universe will keep expanding. Background radiation will keep cooling. The overall energy density will decline. Regions that are not bound will be stretched apart more and more. In this far future, most active processes will be slow. Galaxies, if they still exist as distinct entities, will be quiet. Star formation will have dwindled. Gas suitable for making new stars will be depleted or locked up in inert structures. The sky, as seen from any surviving planets, will be dark, perhaps illuminated by a few dim remnants or the occasional flare from a rare interaction, but the patterns of bright constellations familiar today will long since have been erased as stars drifted and died. The overall impression would be one of loneliness and stillness, on a scale difficult to express. This idea of a universe growing lonely is not just metaphor, it is a direct consequence of accelerated expansion. And finite resources, acceleration, driven by dark energy, ensures that distant galaxies cross beyond causal contact. Even if we had perfectly efficient means of travel or communication, we could not keep up with the speed at which space expands on those scales. Meanwhile, the reservoirs of free energy, that power structure, are consumed. Stars use up their fuel. Matter settles. Radiation redshifts. Each process takes the universe one step closer to a more uniform, less structured state. If heat death is the final equilibrium, then this long era of fading light and increasing isolation is the approach, the long twilight before near darkness. Yet, even this picture contains a kind of quiet beauty. There is no sudden catastrophe, no instant collapse. Instead, there is a gradual ebbing of activity, spread over timescales that dwarf the lifespan of stars and of life. The processes are gentle on their own scale. Thermal energies decline, collisions grow rarer, events become infrequent, until the cosmos is more like a vast, cold, rarefied mist than a blazing display of galaxies and stars. For beings who exist now, this deep future is not something to fear. It is so remote that it lies beyond any practical concern. But as an object of thought, it helps us understand where the laws of physics point when we extrapolate them far beyond our present moment, the expanding universe. That we observe through telescopes, through redshifts, through the cooling microwave background, is not just a snapshot. It is part of a trajectory from a hot, dense early state to a cold, sparse late state. Along this trajectory, space stretches, galaxies recede, radiation cools, and the night sky as we know it gradually empties, leaving behind a quieter, lonelier, but still lawful cosmic sea, within which heat death becomes not a sudden event, but the natural culmination of a very long, cool, and gentle drift toward equilibrium. Far from the familiar glow of our local star, across the deep fabric of space, the universe is filled with structures, stars, galaxies, star clusters, and black holes. All of them are temporary arrangements of matter and energy. All of them are shaped by gravity, by nuclear physics, by radiation, and by time. To understand how the cosmos slowly unravels, we need to understand how these structures are born, how they live, and how they eventually fade. Begin with a cloud, a vast, cold, diffuse cloud, made mostly of hydrogen gas with a smaller fraction of helium and traces of heavier elements. These clouds float within galaxies shaped by gravity, by turbulence, and by magnetic fields. At first, the gas may be spread out so that gravity is weak. Thermal motion, the random jostling of atoms and molecules, helps to support the cloud, preventing it from collapsing. But if a region becomes slightly denser, gravity there grows stronger, it pulls in more gas. The denser it becomes, the more it attracts. This positive feedback can cause parts of the cloud to contract, forming clumps. As the clumps shrink, gravitational potential energy is converted into heat. The gas in the core becomes warmer, its particles move faster, pressure rises. Eventually, if enough mass is gathered, the central temperature and density become high enough for nuclear fusion. Hydrogen nuclei begin to fuse into helium, releasing energy in the form of photons and neutrinos. This energy generates outward pressure, balancing the inward pull of gravity. The object has become a star. Every star represents a delicate balance between gravity pulling matter inward and pressure driven by fusion, pushing outward. If gravity wins decisively, the star collapses. If pressure wins, the star expands in a stable star. The two are in near equilibrium. A quiet tension, sustaining a luminous sphere for millions or billions or even trillions of years. The details depend on mass. Mass is destiny for stars, small stars, with perhaps a tenth of the sun's mass. Burn their fuel slowly. Their cores take their time, converting hydrogen to helium. They can live for trillions of years, outlasting larger stars by huge factors. Stars like the sun, with roughly one solar mass, burn more quickly. Their main sequence lifetimes are measured in billions of years. Massive stars, with 10 or 20 or more times the mass of the sun, live intensely. Their cores reach higher temperatures. Fusion proceeds rapidly. They shine brilliantly, but they exhaust their fuel in just millions of years, a brief flash on cosmic timescales. While stars live, they are engines turning simple elements into heavier ones. In the cores, hydrogen fuses to helium. Later, helium can fuse into carbon, oxygen, and other elements. In massive stars, fusion stages can continue, building elements all the way up to iron. With each stage, energy is released, supporting the star against collapse, and at the same time enriching the stellar interior with heavier nuclei. The story of stars is the story of element formation. The carbon in your body, the oxygen in your lungs, the calcium in your bones were forged in stars and released when those stars died. Stars do not live alone. Gravity weaves them into larger structures within a galaxy. Stars orbit a common center, guided by the combined mass of stars, gas, dark matter, and dust. Disk galaxies display spiral arms, regions where density waves compress gas, triggering new star formation. Elliptical galaxies contain older stars with smoother, more featureless distributions. Dwarf galaxies hold fewer stars, but they are numerous, scattered like small islands. Within the larger archipelago of galactic structures, galaxies themselves are not isolated. They gather into groups and clusters. Within clusters, dozens, hundreds, or even thousands of galaxies orbit a shared center. Between clusters stretch long filaments of galaxies and gas, forming a vast cosmic web. On the largest scales, this web displays patterns of nodes, filaments, and great voids where few galaxies reside. This structure is shaped by gravity. Acting over billions of years on tiny fluctuations in the early universe, regions slightly denser than average attracted more matter, becoming seeds of future galaxies and clusters. Over time, they drew in gas and dark matter, forming deep gravitational wells in which stars could form and shine. Even though galaxies and the cosmic web look like order, they exist within an environment where entropy is increasing. Gravity seems at first to run counter to disorder. It pulls matter together, forms clumps, creates structure. But when we consider the system as a whole, these processes also contribute to the growth of entropy. As gas falls into galaxies, it heats up, random motions increase, radiation is emitted, carrying entropy away. When stars form, they create regions of low-entropy matter, but they also shine, emitting photons that spread energy over large volumes. Those photons carry entropy into the wider universe. The interplay between gravitational clumping and radiative dissipation leads to a complex dance in which structure coexists with and helps produce higher entropy states. Eventually, stars exhaust their central fuel. For a star like the Sun, once the hydrogen in the core is mostly converted to helium, fusion in the core slows. Gravity causes the core to contract. The outer layers respond by expanding. The star becomes a red giant. In this phase, hydrogen fusion continues in a shell around the core, and if conditions allow, the helium core itself can begin to fuse into heavier elements. Later, the star sheds its outer layers, creating a planetary nebula, a glowing shell of gas, expanding away from the dying star at the center. The core is left behind as a white dwarf, a compact object, roughly the size of Earth, but with a mass comparable to the Sun, supported not by thermal pressure, but by quantum mechanical effects. In the electron gas, over very long times, this white dwarf will radiate away its heat, cooling, becoming dimmer until it is effectively dark, a cold cinder in space. More massive stars follow different fates. When their cores build up iron, fusion can no longer release energy from iron and heavier elements. Fusion tends to absorb energy rather than produce it, so when the core is dominated by iron, the star loses its main energy source. Gravity wins. The core collapses. In a fraction of a second, temperatures and densities skyrocket. A shock wave forms, rippling outward through the overlying layers. The star explodes as a supernova. For a brief time, it can outshine an entire galaxy. In that explosion, heavy elements are flung into space, enriching the interstellar medium with material that can later be incorporated into new stars, planets, and perhaps life. The collapsed core survives as a neutron star or a black hole, depending on mass. A neutron star is a sphere just a few tens of kilometers across, with a mass similar to the Sun. Its density is so high that matter is packed into a state where atomic nuclei have been crushed together. The interior is dominated by neutrons. Neutron stars spin, carry intense magnetic fields, and can emit beams of radiation. Observed as pulsars over time, they too cool and spin down, becoming quieter, remnants in the dark. If the collapsing core is massive enough, not even neutron pressure can halt gravity. The core collapses, past a critical radius, forming a black hole. Black holes are regions of space-time where gravity is so intense that not even light can escape. They are bordered by an event horizon, a surface that marks the boundary between regions that can communicate with the outside universe and regions that cannot. From the outside, a black hole is characterized by just a few quantities: its mass, its spin, and its electric charge. In most astrophysical situations, charge is negligible, so mass and spin define the object, but there is more to a black hole than its simplicity suggests. We now know that black holes carry entropy and have a temperature. The entropy of a black hole is proportional to the area of its event horizon, measured in units of the Planck area, an unimaginably tiny scale. the number of microscopic states associated with a black hole is enormous. Even a black hole, with the mass of the Sun, has an entropy far greater than that of a star of the same mass. More massive black holes have even larger entropies. This means that when matter and radiation fall into a black hole, the total entropy of the universe can increase dramatically. Black holes act as powerful sinks for entropy, gathering disorder from their surroundings and storing it in their horizon area. This is one reason why black holes are central to discussions of the universe's long-term entropy budget. Black holes also have temperature, though it is usually extremely low. Quantum effects in curved spacetime imply that black holes emit radiation, known as Hawking radiation, from a distance. It appears as if black holes are slowly glowing with a thermal spectrum. This radiation carries energy away, causing the black hole to lose mass. The rate is extremely small. For black holes of stellar mass or larger on human timescales, they are effectively stable, but over fantastically long durations, far exceeding the current age of the universe. Hawking radiation can cause black holes to evaporate, shrinking and eventually disappearing into a final burst of radiation. In this way, even these most compact and seemingly permanent objects are transient. They, too, contribute to the universe's drift toward a state where energy is more evenly distributed in low-energy photons and particles. Now, step back and follow the cosmic story. On large scales, at early times, gas falls into gravitational wells, forms stars. Stars light up galaxies. Galaxies clump into clusters. The cosmic web grows more pronounced within galaxies. Star formation proceeds in bursts. Clouds collapse. Stars are born, live and die. Supernovae explode. Driving shocks that stir gas trigger new generations of stars and spread heavy elements throughout space. Black holes at galactic centers accrete matter, shine as quasars and active galactic nuclei. Their energetic jets and radiation, heat surrounding gas, regulate star formation. All of these processes are dynamic and complex. But over billions of years, the reservoirs of cold gas available for star formation are gradually depleted. Some gas is locked into long-lived stars, some is expelled from galaxies by energetic winds. Some is heated and held in extended halos where it cools slowly. The overall rate of new star formation in the universe peaks relatively early and then declines. We are living in a cosmos where star formation is already less vigorous than it once was in the far future. This decline becomes more extreme. Star formation slows, then nearly ceases. Most matter resides in remnants, white dwarfs, neutron stars, black holes, and in low-mass, long-lived stars that eventually also exhaust their fuel. As these processes play out, entropy rises. Each fusion reaction in a stellar core converts low-entropy nuclear fuel into higher-entropy radiation. Each supernova sends out a storm of photons and neutrinos, carrying entropy to great distances. Each accretion event into a black hole increases the horizon area, and thus the entropy stored there. Order, in the form of stars, planets, and galaxies, coexists with and contributes to an overall trend toward more ways for the universe to arrange itself towards states that are more probable given the constraints of energy and gravity. Over time, the balance shifts from bright structures to dark remnants, from hot stars to cold cinders, from organized flows to sparse, random motions. The large-scale expansion, driven by dark energy, separates bound regions, makes interactions between distant structures less likely. The universe becomes like a city whose lights are going out one by one. Windows that once glowed fade to black until only a few embers remain, and then even they are gone. Emotionally, this picture can feel heavy, a universe cooling and dimming, structures dissolving into a thin, cold background. Yet from a physical standpoint, it is a natural outcome of the same rules that govern everyday thermal processes. The same second law that explains why heat spreads in a cup of tea also explains why galaxies will one day grow quiet. The same gravitational physics that pulls clouds into stars also leads to the formation of black holes, whose evaporation returns energy to diffuse radiation. The life cycle of stars, galaxies, and black holes is not separate from heat death. It is the path the universe takes on its way there: birth, shining, collapse, remnant, and finally, evaporation. Each stage adds entropy. Each stage transforms energy from concentrated and useful forms into forms that are more spread out, less capable of driving further change. In the end, what remains is not nothing, but a very different cosmos, where the structures that once filled space have been smoothed out into a nearly uniform sea, a cosmos that has written its story of light across unimaginable spans, and then, gently, laid down into the long, cool rest of near equilibrium. Imagine the universe not as it is now, but as it will be. After an almost unimaginable stretch of time, long after the last new stars have formed, long after familiar galaxies have dimmed, long after black holes have dominated and then slowly faded, what does it mean to say that such a universe has reached heat death? The phrase can sound dramatic, but in physics it refers to something subtle, a quiet thermodynamic state where there are no large differences in temperature, no strong gradients of energy, no reservoirs from which ordered motion and complex processes can still be powered. It is less an explosion and more a settling into equilibrium. In thermodynamics, equilibrium is the state in which macroscopic properties stop changing with time. Temperature, pressure, density all become uniform or nearly uniform. On large scales, there are still microscopic motions, particles still move, photons still travel, quantum fields still fluctuate, but there are no imbalances that can be harnessed. To do work, no hot object next to a cold one, no compressed gas waiting to expand, no chemical gradients feeding metabolism. In such a universe, entropy has reached or nearly reached its maximum possible value, given the total energy, the total volume, and the laws that govern matter and fields. This is what physicists mean by heat death, a cosmos that has relaxed into the most probable state allowed by physics, a state where nothing interesting, on large scales, can still happen, not because motion has stopped, but because change no longer has direction. To see how the universe approaches this state, it helps to think again about energy gradients. Every engine relies on a difference, a hot region next to a colder one, a high-pressure reservoir next to a low-pressure space, an organized configuration that can move into a more disordered one when energy flows. From high to low, we can extract work, we can build machines, maintain living cells, drive chemical reactions. All of this requires that the universe not be in equilibrium. Some parts must be hotter than others, some parts must be denser or more structured than others. Right now, that is true. Stars are much hotter than interstellar space. Galactic cores are different from the voids between galaxies. Planets have hot interiors and cooler surfaces. Our own bodies maintain internal order by exporting entropy into the environment. But over time, these contrasts fade, stars radiate until their fuel is exhausted. Hot regions cool as they share energy with colder surroundings. Gravitational wells exchange energy with the wider universe. The overall trend is toward a state where energy is spread out as evenly as possible, and where almost all of it resides in low-energy radiation and very dilute particles. To understand this, more concretely, follow the far future. Step by step, we begin. In a universe, much like the present one, galaxies, star clusters, interstellar gas, dark matter halos, black holes, and the cosmic web. Over the next tens of billions of years, star formation continues to slow. The remaining cold gas in galaxies is gradually turned into stars or blown out by stellar winds and black hole activity. Most of the bright, blue, short-lived stars have already formed and died. Only longer-lived stars, like the Sun and smaller red dwarfs, remain as time stretches into hundreds of billions of years. Even these stars move through their life cycles. A star like the Sun expands into a red giant, sheds its outer layers, and leaves behind a white dwarf. Smaller stars burn more slowly, but eventually they too exhaust their nuclear fuel. The rate of new star birth drops toward zero. The universe transitions from being dominated by active, nuclear-burning stars to being dominated by stellar remnants, white dwarfs, brown dwarfs, neutron stars, black holes, and a thin background of ordinary gas and dust. White dwarfs are initially hot, their surfaces glow with residual heat from the star's former life, but they no longer generate energy through fusion, they simply cool, radiating away their thermal energy into space. The timescale for a white dwarf to cool down to very low temperatures is enormous, far longer than the current age of the universe, but given enough time they will fade, from shining embers to cold, dark objects. Physicists sometimes refer to these fully cooled remnants as black dwarfs, dead stars that no longer emit significant light. Throughout this cooling, entropy increases. The thermal energy stored in the compact star is spread out into a larger volume in the form of lower energy photons, filling the universe with a faint, increasingly cold radiation background. Neutron stars, also cool. Initially, their surfaces can be extremely hot. They radiate X-rays and sometimes emit beams of radio waves. But over long durations, they too lose their residual heat, spin down, as they radiate energy and interact with surrounding fields. Their magnetic fields weaken, their emissions diminish. Eventually they become cold, compact relics, rotating slowly in the dark. If certain speculative processes, such as proton decay, are possible, then over even longer times, the very matter inside white dwarfs and neutron stars may gradually break down into lighter particles and radiation. This would further increase entropy by converting dense, ordered forms of matter into more diffuse, high-entropy products. Even if such decay does not occur, gravitational encounters between stellar remnants can eject some from galaxies or send others into black holes, redistributing mass and spreading energy across larger volumes. Black holes play a special role. In this story, they represent states of extremely high entropy. For a given mass, when matter and radiation fall into a black hole, the area of its event horizon increases, and with it, the black hole's entropy. At relatively early cosmic times, supermassive black holes in galactic centers grow by accreting gas, stars, and sometimes other black holes. As galaxies merge, central black holes can coalesce, forming even larger ones. During this era, black holes act as sinks for low-entropy matter, concentrating mass while increasing overall entropy. They are, in a sense, entropic mountains embedded in space-time. However, black holes are not perfectly stable. Quantum field theory in curved space-time predicts that they emit radiation with a thermal spectrum. This Hawking radiation is very weak for massive black holes, but it is not zero. The power emitted is inversely proportional to the square of the black hole's mass. So small black holes evaporate more quickly. Large ones evaporate incredibly slowly. In a universe that is otherwise growing colder, Hawking radiation makes black holes act as very cold objects, radiating even colder photons into a colder background. Over time, this radiation carries away mass. The black hole gradually shrinks and its temperature rises in the final phases. When the black hole has lost most of its mass, the evaporation accelerates until it ends in a brief, intense emission of high-energy particles. All of the mass that had fallen in is effectively returned to the universe in a highly disordered form, both as photons and as other particles. In this process, entropy does not decrease. The area of the horizon shrinks, but the radiation produced carries enormous entropy. The total still increases. By the time the last black holes evaporate, the universe is extremely old, on the order of timescales so long that words like billion or trillion are completely insufficient to capture them. But the qualitative picture is clear. One by one, the great entropic reservoirs of black holes dissolve into diffuse radiation and light particles. At this stage, almost all matter exists as very low-density, elementary particles and photons spread out over an enormous volume. Dark matter, if it is stable, also persists, but becomes increasingly dilute. Any remaining bound structures have either merged into remnants or been disrupted by gravitational encounters. The effect of cosmic expansion guided by dark energy is to stretch space at an accelerating rate. Distant regions recede from one another, faster and faster beyond a certain distance. Light emitted now will never reach us. These horizons limit causal contact between different parts of the universe from any given vantage point. The observable region becomes an island surrounded by zones that are moving away too quickly to ever exchange information. Within each such island, matter and radiation continue to evolve toward local equilibrium. Energy is redistributed. Temperatures fall, gradients flatten, processes that could sustain complexity grow rarer and then essentially impossible. When we speak of the end of physical processes, in this context, we mean the end of processes that rely on free energy. Free energy is the portion of energy that can be converted into work. It is what engines need, what living systems require to maintain order in a universe at or near equilibrium. Free energy is minimal. Most of the energy is in forms that cannot be usefully extracted because everything is at nearly the same temperature or because the density is too low. To permit effective interactions, particles still collide, but only rarely and without large-scale effects. Photons still propagate, but there is no organized source pumping out radiation against a cold background. Instead, the background itself is the dominant pattern, a thin bath of extremely long wavelength photons and a sparse gas of lightweight particles, like electrons, positrons, and perhaps neutrinos, if proton decay or related processes are allowed. Most composite particles have already decayed, leaving behind only the lightest, most stable species. If such decay is forbidden, protons may persist, but they are spread so thinly that meaningful interactions are exceedingly rare. Either way, the capacity for complex chemistry, for star formation, for planet building, and for life has essentially vanished. It is important to emphasize that this does not mean motion stops on microscopic scales. Quantum fluctuations continue. Particles still possess kinetic energy. There may be occasional, scattered collisions and quantum events, but there is no systematic way to harness these motions, to build new structures or maintain existing ones. From the standpoint of thermodynamics, the universe has reached the state that maximizes entropy, given its constraints. There is no direction left to move that would increase entropy in any significant way. And because the arrow of time is deeply linked to entropy increase, the passage of time in such a universe loses its familiar character. Moments are no longer distinguished by large-scale change. The cosmos, on any human-accessible scale, looks essentially the same from one enormous span to the next. From a distance, we can imagine this final state as a kind of cosmic twilight, but even that is too vivid. The actual picture is more like a universe faded to nearly uniform gray. If we could translate the extremely low-energy photons into visible light, we might see a faint, uniform glow with no bright points, no galaxies, no nebulae, no swirling disks, just a smooth, featureless field of radiation and a sprinkling of isolated particles separated by huge distances. In such an environment, there is no surface to stand on, no sky to look up at, no stars to navigate by, only a quiet, statistical state of matter and energy, the final act of a universe that has spent its entire history, transforming gradients into equilibrium, patterns into randomness, and low-entropy configurations into high-entropy ones. From the human viewpoint, this can sound bleak, a universe that began hot, dense, full of potential, evolving ultimately into a state where nothing more can happen. But from the perspective of physics, it is simply the natural outcome of laws that treat all microstates with equal weight. High-entropy states are overwhelmingly more numerous than low-entropy ones. It is therefore unsurprising that given time, systems drift and then settle into those states. The heat death of the universe is just that idea, scaled up from cups of tea and cooling stars to the cosmos itself. In this light, the rich structures we see today are not the baseline, they are the exception, temporary islands of low entropy carved out within a larger sea of increasing disorder. Our era is one of many phases in which the universe was far from equilibrium, an era where gradients abound and free energy is available to power movement, complexity, and life. Eventually, these gradients will fade, not quickly, not soon, but gradually, relentlessly, across timescales that dwarf the entire history of our species and our planet. When the last remnants of structure have dissolved into this thin, quiet background, the universe will not be a place of drama, it will be a place of near-perfect balance. Everywhere you go, conditions will be similar. Every direction will look the same. Every large volume will contain roughly the same, smooth mixture of low-energy quanta. There will be no preferred locations, no preferred directions, no preferred epochs. It is, in a way, a final expression of the cosmological principle, the idea that on the largest scales the universe is homogeneous and isotropic. Only now, homogeneity and isotropy are not approximations, they are the defining features of the cosmic state. In that distant future, the story of becoming is effectively over. The story of being stretches on as a quiet, almost featureless continuation of an equilibrium reached at last by a universe that has run out of ways to further increase entropy. The heat death is not an event, but a limit, a boundary, that evolution as we understand it approaches ever more closely until the distinction between before and after loses its meaning, and what remains is simply a vast, still cosmic sea. Imagine that the future of the universe is not a single inevitable path, but a branching set of possibilities, each one rooted in the same physics, yet diverging based on subtle details in how space, time, and energy behave. Heat death is one of these paths, a quiet, ever-cooling approach to equilibrium, but it is not the only scenario that cosmologists have considered. To understand what might come, it helps to walk slowly through some of the alternatives, one by one, gently, carefully, without drama, just following the logic of the laws of nature. As far as we can, begin with a possibility, often called the Big Rip. In our current understanding, the universe is expanding, and that expansion is accelerating. The driver of this acceleration is something we call dark energy, an unknown component with negative pressure that pushes space to expand faster over time. In the standard picture, dark energy behaves like a constant background. Its density stays nearly the same, even as space grows. This leads to a smooth acceleration. Galaxies drift apart, but structures that are gravitationally bound, like galaxy clusters, galaxies, solar systems, remain intact. They feel expansion, only indirectly. But there is a more extreme idea. Suppose dark energy does not remain constant. Suppose its density increases with time, or its properties change in a way that makes its repulsive effect stronger and stronger. If that happens, then the expansion could accelerate, not just gently, but violently. In this case, there comes a time when the outward push of dark energy becomes strong enough to overcome gravity, even on smaller scales. First, galaxies would drift out of one another's reach. Then, individual galaxies could be pulled apart, their stars no longer held tightly by collective gravity. Later still, star systems could be torn apart, planets and their stars separating, because the very fabric of space is stretching too rapidly. In the most extreme phase, even atoms could be torn apart. The bonds that hold nuclei and electrons together would be overwhelmed by the accelerating expansion. Matter itself would be shredded, not by collisions, but by the stretching of space-time. This is the Big Rip, a universe where expansion becomes so powerful that it dissolves structures at every scale, ending not in quiet equilibrium, but in a final rapid disintegration of all bound systems. The timing of such a process would depend on the details of dark energy. If its effective pressure becomes strongly negative, the rip could occur in a finite time, measured from today, but our best current observations do not require such extreme behavior. They allow it as a mathematical possibility, but they do not demand it. The Big Rip is therefore a scenario viewed with caution, interesting but speculative, a reminder that the future of the universe is tightly linked to the precise nature of dark energy, which we still do not fully understand. Now turn to a very different vision. Instead of accelerating forever, imagine that cosmic expansion slows, stops, and reverses. In this picture, the universe does not expand endlessly, but eventually reaches a maximum size and then begins to contract. Distances between galaxies start to shrink. Light traveling through space is no longer stretched but compressed. Temperatures rise, densities increase. Over time, galaxies, clusters, and larger structures move closer. Gravitational interactions grow stronger. Events become more frequent and more energetic. As contraction continues, the universe becomes hotter, denser, more uniform. The direction of change now runs opposite to what we see in the early stages of expansion, but the underlying physics is the same. If contraction continues all the way to extremely high densities, the cosmos could end in what is sometimes called a big crunch, a state where spacetime itself collapses into a hot, dense final condition. In some models, this final state is not truly an end, but a bridge to another beginning. After a crunch, there could be a bounce. Instead of terminating in a singular point, the universe might re-expand from a dense phase into a new cycle of expansion, cooling, structure formation, and perhaps another contraction far in the future. This gives rise to cyclic models, where the universe has no single origin or final end, but experiences repeated phases of growth and collapse, each cycle stretching across huge spans of time. In such cyclic scenarios, entropy plays a delicate role. With each cycle, entropy tends to increase, so mechanisms must be introduced to dilute or reset it. Perhaps during each phase of accelerated expansion, entropy is spread over larger and larger volumes, allowing new cycles to begin in a relatively low entropy state compared to the maximum possible. The details are technically subtle, and many proposed models face challenges from both theory and observation. Still, the idea of a universe that breathes, rather than simply fades, has a deep conceptual appeal. It connects endings with beginnings, turning the cosmic story into a repeating rhythm, rather than a single arc from origin to extinction. There are also visions that do not focus on the global expansion or contraction of a single universe, but instead consider the possibility of many universes existing in a broader framework, sometimes called a multiverse, in one set of ideas. Associated with eternal inflation, different regions of a larger space-time can undergo rapid expansion at different times. Some regions stop inflating, cool, and settle into universes with physical properties like our own. Others continue inflating, producing more regions in an ongoing process. Within this picture, our universe is like a bubble in a much larger foamy structure. Each bubble may have different values of physical constants, different particle contents, different histories. The concept of heat death still applies within each bubble. Over time, entropy increases, structures form, evolve, and decay, until each bubble universe approaches its own high-entropy fate. But on the larger scale of the multiverse, the process of bubble formation may continue indefinitely. New low-entropy regions constantly emerge, even as older ones age toward equilibrium. From this perspective, heat death is not the end of all that is. It is the end of a particular domain, while elsewhere, new beginnings are unfolding quietly beyond any horizon we could ever see. Quantum theory adds more layers of possibility to these speculative futures. Even in a universe at or near equilibrium, quantum fields do not sit perfectly still. They fluctuate randomly around their minimum energy states. In some models, these fluctuations can occasionally be large enough to create small, temporary departures from equilibrium. In very rare circumstances, they might even assemble complex configurations of matter or entire regions that resemble a low-entropy patch, like the early observable universe. However, such events would be fantastically improbable, overwhelmingly dominated by much simpler fluctuations. This line of thought raises subtle questions about probability, typicality, and what it means to describe the future of an infinite or extremely long-lived cosmos. It also leads to paradoxes, such as the notion of isolated conscious observers arising spontaneously from fluctuations rather than from cosmic history. These possibilities are taken seriously enough to be discussed in technical literature, but they also highlight how far our intuition is stretched when we combine quantum mechanics, statistical physics, and cosmology at the most extreme limits. Another speculative avenue involves the idea of vacuum decay. In quantum field theory, the vacuum is not simply empty space. It is a state with certain energy and structure. In many models, there can exist multiple possible vacua with different energies. Our universe may be in a vacuum state that is stable or only metastable. If it is metastable, then there is a non-zero, though possibly tiny, probability that it could someday transition to a lower energy vacuum. Such a transition would proceed by the formation of a tiny bubble of the new vacuum at some location. This bubble would then expand at nearly the speed of light, transforming the vacuum and the laws of physics inside it as it passes through a region. Particles, forces, and even the structure of atoms might change in ways incompatible with existing matter from the viewpoint of any observers. In the old vacuum, this would be a sudden catastrophic event without warning, because the front of the bubble would arrive at nearly light speed. Cosmologically, vacuum decay would rewrite the late-time behavior of the universe, perhaps altering whether heat death or some other fate is realized or transforming the cosmos into a very different physical regime. The likelihood and timescale of such an event depend on the detailed shape of the quantum fields that define our vacuum. At present, we do not know whether our vacuum is truly stable or only long-lived. Over enormous durations, again, we encounter a scenario that is technically plausible, yet deeply uncertain and observationally unconstrained. Given this wide landscape of speculative futures, why do cosmologists so often return to the picture of heat death as the leading scenario? The reason is not that other ideas are impossible. It is that heat death follows rather directly from the simplest reading of current data and well-tested physics. We observe that the universe is expanding and that this expansion is accelerating. The simplest model that fits these observations assumes a cosmological constant, a form of dark energy with constant density and constant equation of state. Within this framework, space expands forever, The density of matter dilutes bound structures, remain bound locally, but on the largest scales, regions drift out of causal contact, entropy increases, black holes form, and eventually evaporate. Matter and radiation spread out until the universe becomes cold, dark, and nearly empty. This is the heat-death scenario. It uses no exotic assumptions beyond those already needed to describe our current observations. It is, in that sense, a conservative extrapolation of what we know into what we do not yet see. By contrast, the Big Rip requires dark energy to evolve in time in a particular way. Cyclic models need mechanisms to reverse expansion and manage entropy. Vacuum decay depends on details of high-energy physics we have not yet measured. Multiverse pictures extend inflationary theory into realms far beyond direct test. None of these are ruled out, but each introduces additional hypotheses, additional structure beyond what is strictly required to account for existing data. So for now, heat-death remains the reference case, the baseline story of a universe that cools, dilutes and settles into maximum entropy under the combined influence of expansion, gravitation, quantum effects, and thermodynamics. Yet even within this baseline, there is room for a kind of quiet imagination. Alternative futures may not manifest on grand dramatic scales. They may instead be encoded in how the universe approaches equilibrium. Does dark energy remain constant or slowly evolve? Do new forms of physics emerge at ultra-low energies? Do quantum effects in curved space-time modify our expectations at unimaginable timescales? These questions do not turn the future into a catastrophe. They simply add texture to the long-fade possibilities for subtle differences in a story that is otherwise remarkably simple. And so when we think about alternative cosmic futures, we are not choosing between hope and doom. We are exploring how the same laws of space, time, and energy might play out under slightly different conditions. Sometimes those possibilities lead to images of universes tearing apart, or collapsing and rebounding, or giving birth to new domains beyond our horizon. At other times, they lead back to the same quiet ending, a universe that grows colder, more diffuse, and finally so nearly uniform that nothing more of large-scale structure can occur. In every case, the tone is set not by emotion, but by physics, by the interplay of expansion, gravity, quantum fields, and entropy. We do not yet know, with certainty, which path our universe will follow. We only know that whichever path unfolds, it will be governed by the same quiet mathematical rules that already shape the stars above us and the atoms within us. And as we rest inside one brief moment of this vast process, we can let these possibilities drift across the mind like distant constellations, not as threats, but as gentle reminders of how wide the future really is. Life is an exception, not to the laws of physics, but to their most likely outcomes. If you imagine all the ways matter and energy can arrange themselves in a vast universe, the overwhelming majority of those arrangements are simple, disordered, featureless, atoms spread thinly, temperature nearly uniform, nothing intricate, nothing conscious, nothing that thinks about the future. And yet, on at least one small world, around at least one ordinary star, matter has organized itself into systems that resist, for a while, the smooth slide toward disorder. These systems are alive. A living cell is a structure of remarkable order, molecules arranged in specific patterns, membranes, engines, information stored in long chains of nucleic acids, all of it tuned to maintain a delicate internal state against the constant pull of entropy. To keep this order, the cell must continuously trade with its surroundings. It takes in energy and material. It performs chemical reactions that build, repair, and regulate, and it expels waste, heat, and disorder back into the environment. From the perspective of thermodynamics, life does not break the rules, it uses them. A living system locally decreases entropy inside itself by increasing entropy in the space around it. It is like a tiny island of pattern that survives by exporting its disorder. To the wider sea, this is true of a single bacterium, a tree in a forest, a human brain, even a complex ecosystem on the surface of a planet. Order is maintained by a constant flow of energy from sources like starlight to sinks like the cold background of space. As long as that flow exists, life can persist as a dynamic balance between building up and breaking down, between structure and entropy. Consider your own body at this moment. Billions upon billions of cells are carrying out chemical reactions every second. They are replacing damaged molecules, maintaining gradients across membranes, sending electrical signals along nerves. All of this consumes energy from the food you have eaten and from the oxygen you breathe. The energy enters in a relatively low entropy form, concentrated in chemical bonds. It leaves as heat, more diffuse, spread into many degrees of freedom. In this way, your continued existence as an organized being relies on entropy increasing. In the environment, Earth as a whole is similar. It receives energy from the sun in the form of light. At relatively high temperature, it re-radiates energy back into space in the form of thermal infrared. At lower temperature, the difference allows work to be done, weather patterns to circulate, chemical cycles to turn, and life to persist. The planet is like a heat engine running on sunlight. The biosphere is one of its emergent products, a tapestry of low-entropy structures, maintained by the constant flow of energy from hot star to cold space. Seen in this light, life can be viewed as a temporary strategy of the universe to explore the possibilities of complexity, under the constraint that entropy, overall, must increase. As long as there are gradients in temperature or chemical potential or radiation density, there is room for complex systems to form, to persist, and to change. When those gradients vanish, so does the possibility of that kind of complexity. In a universe drifting toward heat death, the energy differences that power life and thought and technology slowly fade. Starlight dwindles, chemical-free energy is exhausted, the background becomes more uniform, more featureless. It is not that the laws of physics change, it is that the conditions for low-entropy structures no longer exist on large scales. To feel the weight of this trajectory, it helps to compare human time with cosmic time. Most of your experiences unfold on scales of seconds, minutes, hours. A deep conversation might last a few hours, a day, or an evening. A meaningful relationship might unfold over years or decades. A human lifetime spans roughly 10 decades, 100 years, give or take. Even the longest human institutions, civilizations, languages, religions, typically span, at most, thousands of years, perhaps tens of thousands. When we push further, our recorded histories reach back some tens of thousands of years. The existence of our species, as anatomically modern humans, is measured in hundreds of thousands of years. Mammals have existed for tens of millions of years. Complex multicellular life for hundreds of millions. Life on Earth, as a whole, for on the order of billions of years. Already, these scales begin to strain. Everyday intuition, to many people, a million years feels almost indistinguishable from eternity. Yet in cosmology, these durations are still tiny. The age of the observable universe is roughly 14 billion years, that is, 14,000 million years. If you tried to count 1 year per second, you would need about 440 years of continuous counting, just to say 14 billion out loud. If you imagine the entire age of the universe so far compressed into a single year, then each month would be a little more than 1 billion years. In that compressed calendar, the formation of Earth would occur around early September. The emergence of simple life would follow, not long after, but complex animals would appear only in mid-December. Dinosaurs would roam in the last week of the year. They would vanish on December 30th. Early human ancestors would show up late on December 31st, and everything we call recorded history, the span from ancient civilizations to the present moment, would occupy only the last seconds before midnight on the final day. That is how small our familiar timescales are compared with cosmic times already elapsed. Yet the timescales, relevant to heat death, stretch far beyond even this. The death of the last stars, the cooling of white dwarfs into black dwarfs, the evaporation of black holes through quantum radiation, these processes unfold over times, measured not merely in billions of years, but in numbers so large that our language struggles to carry them. Durations like 10 to the power of 100 years and more, a 1 followed by 100 zeros. Even writing that number occupies space on a page. In these ranges, comparing human lifetimes to cosmic timescales is like comparing a heartbeat to the age of mountains and then realizing that even mountains are brief against the life of the cosmos. Faced with this contrast, it is natural to ask what meaning our lives can have if the universe is heading toward a state where nothing complex remains, if everything we build and remember and love will be lost. In the end, does it matter? Physics cannot answer questions of meaning in a philosophical sense, but it can offer a perspective. Meaning is not a property of the universe as a whole, it is a property of minds, of systems, capable of experiencing patterns, valuing outcomes, and reflecting on their own existence. These systems are temporary. By their very nature, they are born, they change, they end. That impermanence is not a flaw in the design, it is a necessary consequence of being made of matter and energy, obeying physical laws. In a world where entropy increases, the fact that something will end does not erase the reality of its existence. While it lasts, a melody is real, even though the air eventually grows quiet. A wave in the ocean is real, even though it breaks and disappears. A thought is real, even though it fades. A human life is real, even though it unfolds within a finite span, on a finite world, in a finite region of time. The universe far in the future will not contain your memories or your experiences, but they exist now. They have causal effects, they shape other lives, they generate ripples that move outward through conversations, actions, and relationships until they blend into the larger fabric of history and culture and biology. Impermanence does not erase significance, it is part of what gives experiences their intensity. Knowing that moments will not repeat opens a space for appreciation, for attention, for care. On cosmic scales, memory is stored not only in minds, but in light and matter. Every photon that leaves a star carries information about the conditions in which it was emitted, its energy, direction, and timing, encode details of the star's temperature, motion, and internal processes. When that light travels across space for millions or billions of years, it becomes a kind of archive, a record of how things were long ago. When we build telescopes and detect that light, we are reading old messages sent long before life arose on Earth. The glow of the cosmic microwave background is a fossil. From when the universe was young, only a few 100,000 years old, it carries imprints of density variations that later grew into galaxies and clusters. In that faint, uniform radiation, we are seeing a picture of the cosmos, not as it is now, but as it was in its early youth. Every observation in astronomy is like this, a look into the past, because light takes time to travel. Even nearby stars are seen as they were years ago, distant galaxies as they were millions or billions of years ago. Cosmic memory is distributed in trajectories of photons, in the motions of stars, in the chemical compositions of gas clouds, heavier elements in your own body. Atoms of carbon, oxygen, iron were forged in ancient stars that lived and died long before the sun existed. Their supernova explosions seeded interstellar space with the materials from which new systems would form. In that sense, you are part of the universe's memory, a structure in which history is literally embodied, matter that has passed through many states, now participating in thought and awareness. For a brief time, as the universe evolves toward higher entropy, this cosmic memory becomes more diffuse. Light is redshifted to lower energies. Structures are disrupted. Information is scrambled and spread over larger regions. In some descriptions, information is never truly destroyed. It is only transformed and dispersed. But for practical purposes, it becomes inaccessible. For beings like us, no future observer in a heat-death universe would reconstruct the details of every planet, every life, every thought. But that does not mean those things were insignificant. They were the unique ways in which this particular cosmos explored its own possibilities under its particular laws. There is also a quieter insight. Hidden in the vastness of cosmic time, our concerns are small compared to galaxies and black holes in future eons, but our nervous systems are tuned to the scales on which we live. Your joys and fears and questions are large on that local scale. They occupy the full width of your inner world. Knowing that the universe will one day be cold and dark does not nullify the warmth of a human connection. Tonight, knowing that galaxies will eventually drift beyond one another's horizons does not erase the wonder of looking up at the sky on a clear night and seeing their soft light. The immensity of time and space can feel at first like a threat, as if it were saying, "You are small, you do not matter." But the same immensity can also be experienced as a cushion, a background, against which the details of your life are freed from the burden of being absolute. In a temporary universe, perfection is not required to make moments worthwhile. You are allowed to be a transient pattern, a fleeting arrangement of matter and mind that experiences a narrow band of reality before dissolving back into the larger whole. There is a calm, quiet in accepting this. Scientific understanding helps here, not because it offers comforting stories, but because it clarifies our situation. It tells us we are made of the same particles that fill space, governed by the same forces that shape galaxies. It shows us that life emerges naturally when conditions allow, and that consciousness is not a supernatural intrusion, but a particular way complex matter can organize itself within the rules of physics. It also tells us that those conditions are temporary, that energy gradients fade, that entropy increases, that the universe on large scales is moving towards states where mind and life as we know them cannot exist. Holding these facts together, we can see our own existence as a brief, unlikely, but entirely natural episode in a much larger story. Understanding this can bring a different kind of peace, not the peace of guaranteed happy endings, but the peace of seeing clearly where we stand and of allowing that clarity to soften our compulsive need for permanence. As you lie here listening, you are part of this delicate balance. Energy is flowing through your body, maintaining order against entropy. Your thoughts are patterns in electrical and chemical activity. In your brain, patterns that did not exist a few decades ago and will not exist a few decades from now. Around you, the planet turns, the atmosphere circulates, the sun shines, fusing hydrogen into helium deep in its core. Above that, on grander scales, stars move through the galaxy. The galaxy orbits within a cluster. The cluster drifts through expanding space, all of it part of a universe that is slowly, quietly changing from a hot, dense, young state to a cooler, more diffuse, older one. In that immense, ongoing transformation, your life is a single thread, but it is real. It is here now for as long as it lasts. And in that, there is room for meaning, for curiosity, for kindness, for awe, and for rest. Entropy can feel abstract, but at its core, it is about counting all the different ways a system can be arranged, while still looking more or less the same from far away. Imagine a simple example, a box filled with many tiny particles. They can move, bounce, collide, rearrange themselves. From a distance, you might only care about a few large-scale properties: how much energy is in the box, how many particles there are, what the overall temperature is. That coarse description is called a macrostate, but hidden beneath that simple description are many, many microscopic details. Exactly where each particle is, exactly how fast it is moving, and in what direction. Each precise arrangement is a microstate. Many different microstates can correspond to the same macrostate, the same total energy, the same number of particles, the same temperature. Entropy is a measure of how many microstates belong to a given macrostate. High entropy means there are many ways for the system to be arranged without changing its large-scale appearance. Low entropy means there are only a few. This way of thinking explains why certain states are far more likely than others. Consider all the air in the room around you. The particles of that air are constantly moving, colliding, changing direction. If you asked, what is the chance that all of the air molecules will spontaneously gather in just one corner of the room? The answer is that it is possible, but unimaginably improbable. There are far more microstates, in which the air is spread out evenly, than microstates, where all the air is crowded into one small region. The evenly spread state is a high-entropy macrostate. The crowded state is a low-entropy macrostate, because the system naturally explores all the microstates available to it. It tends to move from low-entropy configurations to high-entropy ones, simply because there are vastly more of them. In this sense, entropy is not a force that pushes things. It is a way of counting, which tells us what is typical and what is extraordinarily rare. When physicists say that a closed system tends to evolve toward higher entropy, they mean that if you allow the system to run freely without external interference, it will almost always move toward macrostates with more possible microstates. It will relax toward what is called equilibrium. Equilibrium is a condition where large-scale properties no longer change on their own. Temperature becomes uniform, pressures balance, flows of matter and energy die down. At equilibrium, the system is still full of microscopic motion. Particles still move, bounce, vibrate, but on average, there are no more large-scale gradients to drive steady change. It is, in a quiet sense, the most probable state available. given the constraints. To talk about how far a system is from equilibrium, physicists use the idea of free energy. Free energy is the portion of the total energy that is available to do work, to drive processes that create or maintain structure. When there are strong gradients, such as a hot region next to a cold region or a chemical mixture, far from balance, the free energy is high. There is potential for organized motion. Engines can run, reactions can proceed, life can sustain itself. As the system evolves toward equilibrium, those gradients diminish, the free energy is converted into heat, spread more widely, entropy increases, and the capacity to do additional work declines. When the system finally reaches equilibrium, its free energy is minimal. There is still energy in the system, but none of it is arranged in a way that can produce coherent change on large scales. In that sense, heat death of the universe is the ultimate equilibrium state on the largest scales, a condition in which free energy has been used up and only random microscopic motion remains. In cosmology, we must think about entropy, not in a fixed box, but in a universe where space itself is expanding. As space expands, light that travels through it is stretched, its wavelength increases, its energy decreases. This effect is called redshift, because light stretched to longer wavelengths often shifts toward the redder part of the spectrum. You can picture this by imagining a wave painted on a rubber band. As you pull the band, the distance between each crest increases, the wave stretches, its pattern becomes less energetic. Something similar happens to photons moving through an expanding universe. Over billions of years, light emitted at high energy from hot stars or from the early universe is redshifted to lower energy. The cosmic microwave background is an example. It began as very energetic radiation when the universe was much hotter. As the cosmos expanded, those photons were stretched again and again, lowering their temperature until today they form a nearly uniform background, only a few degrees above absolute zero. This redshift is part of how the universe shares energy with expanding space. The total number of photons can remain large, but their average energy declines, contributing to the gradual cooling and the increase in entropy on cosmic scales. Expansion also changes how we think about equilibrium. In a fixed box at equilibrium, matter and radiation are evenly distributed at some stable temperature in an expanding universe. The notion of equilibrium is more subtle because the volume is not constant, but even here we can talk about the tendency for energy to become more diffuse, for temperature to drop, and for gradients to weaken over time as galaxies drift apart, as their interactions grow rarer, as light stretches toward longer wavelengths. The universe moves closer to a state where matter and energy are thinned out and uniform to an extreme degree. Among the most intriguing elements of this story are black holes. For many years, they were thought of primarily as simple sinks, regions from which nothing could escape, not even light. But in the 1970s, physicist Stephen Hawking showed that when quantum effects near the event horizon are taken into account, black holes behave as thermodynamic objects. They have a temperature, they have an entropy, and they can emit a faint form of radiation named Hawking radiation. The entropy of a black hole is astonishingly large. It is proportional not to the volume inside the event horizon, but to the area of the horizon itself, measured in units related to the square of the Planck length, which is an extremely tiny distance scale. This suggests that the number of possible microstates corresponding to a black hole is enormous. Black holes are therefore giant reservoirs of entropy in the universe. They represent very high entropy macrostates into which matter can collapse as they sit in space. Black holes also interact with their environment through Hawking radiation. Quantum fields in the curved region around the horizon can produce pairs of virtual particles. One member of the pair may fall into the hole, the other may escape to infinity. To a distant observer, this looks as if the black hole is emitting particles and gradually losing mass over incredibly long times. The black hole will shrink and eventually evaporate completely, releasing its mass in the form of radiation. This process is extremely slow. For black holes of stellar mass, the evaporation time is far longer than the current age of the universe. For supermassive black holes in galaxy centers, the timescales are even greater. Yet, if we project far enough into the future, beyond the era when new stars form, beyond the era when existing stars have burned out. We reach epochs when black hole evaporation becomes one of the last significant sources of change in the cosmos. As black holes radiate, their entropy is transferred to the surrounding space, increasing the overall disorder while removing the remaining compact structures from the universe. To describe these futures, we must use numbers that strain intuition. The lifetime of an ordinary star like the Sun is around 10 billion years. The smallest and longest-lived stars can shine for hundreds of billions of years. After that era, there is a long time when the remnants of stars, white dwarfs, neutron stars, and black dwarfs dominate that phase, can last for times on the order of 10 to the power of 15 or 10 to the power of 16 years. That is, a 1 followed by 15 or 16 zeros. Later still, black holes begin to evaporate. A black hole, with a mass of a few times the Sun, has an evaporation time around 10 to the power of 67 years. A supermassive black hole, millions or billions of times. The mass of the Sun may persist for timescales of 10 to the power of 80 or 10 to the power of 100 years. These are durations so large that ordinary metaphors fail. If you tried to count each year, one number per second, you would not only outlive any star, you would outrun any conceivable civilization, and you would still not come close to finishing the count. Yet for the universe, such timescales are part of the full story of how entropy is expressed across cosmic history. Early on, entropy increases through processes like nuclear fusion in stars, mixing of gas, and the formation of large-scale structure. Much later, entropy continues to rise through slow interactions between faint remnants and through black hole dynamics. Eventually, even those processes fade, and the universe settles into a state where almost all energy is carried by extremely low-energy photons and perhaps light particles of other kinds, spread thinly through an immense volume with no significant gradients left to exploit. This mathematical picture can sound cold, but it is simply another way of describing the same narrative. We have been following entropy as probability, explains why order is fragile and why disorder is typical. Free energy measures how much potential remains for structure to arise and persist. The expansion of space and the redshift of light show how the universe transforms its early heat into late-time coolness. Black hole thermodynamics reveals that even the darkest, most compact objects participate in this accounting, and the cosmic timescales remind us that the path from a hot beginning to a quiet end is long, beyond easy comprehension. Yet through all of this, the same laws apply, the same concepts of energy, entropy, probability, and equilibrium guide the evolution from the first instance to the far future. Understanding these ideas does not require writing equations on a board. It requires only patience and a willingness to imagine many possibilities and to ask which ones are most probable. In that sense, the mathematics of heat death is another form of listening to what the universe finds typical over the longest possible times and understanding gently why stillness is its final resting place. When we talk about the distant future of trillions and trillions of years, it can feel as if we are reaching beyond anything we could ever hope to know, and yet our picture of that remote future is not built from imagination alone. It is anchored to quiet signals of light that we can actually observe. Right now, from telescopes, on mountains, on satellites, and soon from even more sensitive eyes in space. If you follow those signals carefully, they tell a story of how the universe has expanded, how it has cooled, how its structures have grown, and how, if the same physical laws continue to hold, it is likely to drift toward a state of extreme thinness, high entropy, and deep quiet. The path to that conclusion runs through data, through measurements of radiation, of galaxies, of exploding stars. It is through those observations that we link the physics of today to the forecasting of cosmic tomorrow. One of the most important signals is a faint glow that fills the sky in every direction. It is not visible to your eyes directly because its light has been stretched to wavelengths far longer than the sensitivity of human vision. But with radio receivers and microwave detectors, we can hear it as a soft background whisper. This is the cosmic microwave background, a field of ancient photons, left over from a time when the universe was very young and very hot. Imagine the cosmos roughly 380,000 years after its beginning. At that point, it was filled with a dense plasma of light, electrons, and protons. Photons were scattered constantly by charged particles. Light could not travel freely. It was as if the entire universe was a bright, opaque fog. As the cosmos expanded, it cooled. Eventually, the average energy of the photons dropped enough that electrons could combine with protons to form neutral atoms, mostly hydrogen. Once neutral atoms formed, the fog cleared. Photons could stream across space without being constantly scattered. The cosmos became transparent. Those first free-streaming photons have been traveling ever since. Stretched and cooled by the expansion of space, they are the photons we now detect as the cosmic microwave background. Today, this background appears with a temperature of about 2.7 degrees above absolute zero, almost perfectly uniform, across the sky with tiny variations in temperature and intensity from place to place. Those tiny variations are not noise. They are imprints of the early universe, slight overdensities and underdensities, regions that were a little bit hotter or a little bit colder. These fluctuations are the seeds from which later structure grew. Under the influence of gravity, denser regions pulled in more matter and slowly evolved into galaxies, clusters, and the grand cosmic web of today. By measuring the cosmic microwave background in detail, we can infer fundamental quantities about the universe, its overall geometry, its composition, the relative amounts of ordinary matter, dark matter, and radiation. We can also estimate its age and its large-scale curvature. The data indicate a universe that on large scales is very nearly flat, dominated today by a form of energy that behaves like a cosmological constant, something very similar to what we call dark energy. This information feeds directly into models of how the universe will expand in the future. A nearly flat universe with persistent dark energy expands forever. Its expansion accelerates, gradually separating gravitationally unbound structures and pushing the cosmos toward a state of increasing isolation. Another crucial line of evidence comes from particular kinds of stellar explosions, called Type 1, a supernova. These events occur in binary systems, where a dense white dwarf star steals matter from a companion. As the white dwarf accumulates mass, it approaches a critical threshold, beyond which its structure becomes unstable. The star undergoes a runaway nuclear reaction and explodes in an event of remarkable brightness, because the conditions leading to these explosions are similar from system to system. The peak luminosity of Type 1, a supernova, is relatively uniform. They can act as standard candles, objects whose intrinsic brightness we can estimate if we know how bright they truly are. Then by comparing that intrinsic brightness to how bright they appear to us, we can infer their distance. When astronomers measured the distances to many of these supernovae in distant galaxies and compared them to the redshifts of the host galaxies, they found something unexpected. The galaxies were not simply receding at a rate set by a constant expansion. The expansion itself was accelerating. Distant supernovae appeared dimmer than they would in a universe with only matter slowing expansion. Their light had traveled farther than anticipated, because space had expanded more than a simple model predicted. This discovery was one of the main clues that some form of dark energy is driving and accelerating expansion. Accelerated expansion has direct implications for cosmic fate. If the effect continues into the far future, galaxies that are not gravitationally bound to us or to each other will eventually cross what is called a cosmic event horizon. Beyond that horizon, light emitted will never reach us, no matter how long we wait. It is as if the fabric of space is stretching faster than light can bridge the gap. The observable universe shrinks, in a practical sense, even as the total universe continues to expand. Over time, more and more galaxies slip beyond visibility, leaving only our local group and any structures permanently bound to it. In our sky, everything else fades into the darkness to map how matter is distributed. On large scales, astronomers conduct galaxy surveys. They point telescopes at broad swaths of the sky, measure the positions and redshifts of millions of galaxies, and reconstruct a three-dimensional picture of cosmic structure. From these maps, we see that galaxies do not fill space uniformly. They lie along filaments, walls, and clusters surrounding large voids, regions with fewer galaxies. This pattern is sometimes called the cosmic web. it is a fossil record of how initial fluctuations in the early universe grew under gravity over billions of years. The scale and strength of this clustering depend on the amount of matter in the universe, the nature of dark matter, and the rate of expansion. By comparing the observed patterns with simulations based on different cosmological models, we can constrain which models match reality best. The models that fit these large-scale structures, the cosmic microwave background, and supernova data most successfully are the same ones that point toward a universe dominated by dark energy with an expansion that continues to accelerate. Dark energy itself is still mysterious. We describe it through an effective parameter that relates its pressure to its energy density, called the equation of state. If this parameter is exactly -1, dark energy behaves like a true cosmological constant, a fixed energy density of empty space. If it differs from -1 even slightly, dark energy could evolve over time, leading to different long-term futures, perhaps a slower acceleration, perhaps a faster one, perhaps even a reversal far ahead. To narrow down these possibilities, cosmologists combine many datasets: cosmic microwave background, supernovae, galaxy clustering, weak gravitational lensing, where foreground mass distorts the images of more distant galaxies. Each probe provides constraints on dark energy from a different angle. So far, all signs are consistent with something very close to a cosmological constant. If that holds, then the simplest picture is that the universe will expand forever at an accelerating rate, gradually deepening the isolation of cosmic structures and supporting the idea that heat death is the most probable far future outcome. Yet our measurements are not final. They can be refined. Future observatories on the ground and in space are designed to improve our view of the distant universe. Some will map the cosmic microwave background with higher precision, detecting even smaller temperature variations and subtle polarization patterns. These patterns carry information about gravitational waves from the early universe and about the large-scale structures that photons crossed on their long journey. Others will measure more supernova at greater distances and with better calibration, reducing uncertainties in how the expansion rate has changed over time. Large surveys of galaxies and galaxy clusters will trace structure over volumes far larger than we have today. By watching how clustering changes with redshift, we can see how the tug of gravity competes with the push of dark energy. Weak lensing surveys will use the distortion of many background galaxies to infer the distribution of invisible matter along the line of sight, giving us a three-dimensional map of mass rather than just light. Some missions will study the distribution of hydrogen gas through what is called intensity mapping, measuring the combined signal from many unresolved sources to trace structure on very large scales. Although these projects are focused on understanding the past and present, they help refine our forecasts of the future. If dark energy is confirmed to be very close to a cosmological constant, then extrapolating forward becomes cleaner. We can be more confident that expansion will continue to accelerate, that cosmic event horizons will form, and that structures beyond local gravitationally bound regions will vanish from view. If, however, future data reveal that dark energy varies with time or behaves differently from our simplest models, then alternative cosmic fates may become more plausible. Scenarios like a big rip or a slow change toward different dynamics would need to be considered, again with fresh detail. In this way, telescopes are not only instruments for looking outward, they are instruments for looking forward. Each photon captured on a detector carries information about conditions at a particular time and place in the cosmos. By arranging those photons into patterns of temperature maps, redshift catalogs, and light curves, we build a coherent story of how the universe has behaved and how it is likely to behave later. The faintest signals from the most distant epochs are also quiet messages from our own far future. If you step back and let this sink in, there is a kind of calm in this picture. The equations that describe gravity and expansion, the statistics that describe entropy and structure formation, do not hurry, they do not rush, they simply state that given what we see today, certain paths are more probable than others. We may never watch stars fade on timescales of trillions of years. We may never witness the final evaporation of a black hole. yet the same physics that explains the glow of the cosmic microwave background, the light curve of a distant supernova, and the clustering of galaxies, allows us to extend the curve of the universe's story into epochs far beyond our own. The distant future is therefore not pure speculation. It is an extrapolation from data anchored to real photons. Real measurements, real structures, different observations illuminate different chapters. The microwave background shows us the near beginning, supernovae reveal recent acceleration, galaxy surveys trace the slow growth of structure. Together, they converge on a picture in which an expanding universe dominated by dark energy drifts gradually toward thinness, darkness, and equilibrium, unless some new physics intervenes along the way, lying back. With this in mind, you can imagine each distant galaxy, each cluster, each arc of light in a lensing map as both an island in the present and a marker along a trajectory extending forward. The same observations that show how full and structured the universe is now also indicate how slowly it will empty and smooth out in ages to come. Science becomes a lantern, not only on our past, but on our eventual quiet. It allows you to rest inside a story that is vast, lawful, and continuous, from the first light to the last. Imagine the universe so far in the future that stars have faded, black holes have evaporated, matter is thin, and energy is smeared, almost evenly, across an immense, dark, and quiet cosmos. At first glance, it is tempting to think that this is the end, full stop, a final page on which nothing ever happens again. But when physicists look closely at this extreme, high-entropy state, they find that the story is not necessarily quite that simple. Even in deep equilibrium, there can still be gentle ripples, subtle fluctuations, and speculative possibilities that reach beyond the standard picture of heat death. In statistical physics, equilibrium does not mean that every particle is perfectly still. It means that on average, the properties of the system do not change over time. If you zoom in to the microscopic level, particles are still moving. They collide, they exchange energy, they explore different arrangements or microstates. The reason we call it equilibrium is that the overall distribution of these microstates is stable. The probabilities do not drift, even though individual details continue to fluctuate. In a universe at maximum entropy, something similar may hold. The large-scale structure is flat, homogeneous, and unchanging. But at extremely small scales, quantum fields can still fluctuate. Quantum theory tells us that fields and particles do not have perfectly fixed values. Instead, even in their lowest energy state, they exhibit zero-point motion, a kind of irreducible jitter that cannot be removed. These fluctuations are usually tiny. They average out over large regions, yet they are there, adding a faint shimmer to what might otherwise seem like a perfectly frozen cosmos. One way to picture this is to think of a calm lake on a windless night. To your eyes, from a distance, the surface may appear smooth, flat, almost like glass. But if you were to zoom in to the scale of droplets and molecules, you would find ceaseless motion, water molecules jostling, bumping, rearranging. The lake as a whole is in equilibrium, but at the microscopic level it is alive with thermal motion. In a similar way, a heat-death universe could be macroscopically quiet. And yet quantum fields would still seethe gently at very small scales. Physicists sometimes ask what those fluctuations could do over unimaginably long times. Given enough time, a system exploring all of its possible microstates might occasionally wander into a configuration that is very unusual compared to the typical state. The probability of such a rare fluctuation is extraordinarily small. But the timescales in a heat-death cosmos are extraordinarily large, stretching beyond any human intuition into durations where even events with almost zero probability might still eventually occur. In some speculative scenarios, these rare fluctuations could momentarily assemble complex structures, perhaps a small patch of lower entropy, perhaps a temporary concentration of matter and radiation that briefly resembles a star, a galaxy, or even, in the most extreme proposals, something as complex as a conscious observer. These hypothetical observers, born from random fluctuations in an otherwise high-entropy universe, are sometimes called Boltzmann brains. Not because there is evidence that they actually exist, but because they help reveal a paradox. If they were common, then most observers in the cosmos would be such freak fluctuations, rather than beings who evolved in a low-entropy past. By comparing this idea With our own experiences of living in a universe with rich structure and a long arrow of time, physicists argue that typical observers are almost certainly not fluctuation products, which means either such fluctuations are unimaginably rare even on cosmic timescales, or our understanding of equilibrium and cosmic probability is incomplete. These questions are not answered yet, but they show that even in a universe drifting toward equilibrium, the interplay between entropy, fluctuation, and observation remains subtle. The standard view is still that large-scale heat death means no sustained gradients, no long-lived engines, no enduring complexity. The occasional quantum ripple does not restart cosmic evolution. It flickers and fades against a backdrop of near-perfect uniformity. Beyond fluctuations, another speculative idea involves the concept of vacuum decay. When physicists talk about the vacuum, they do not mean simple emptiness. They mean the lowest energy configuration of the fields that fill space. Our current vacuum appears stable, but in some theories it might be only metastable, not the absolute lowest possible state, but a local minimum in an energy landscape. One way to visualize this is to imagine a ball resting in a shallow valley between hills. From the ball's perspective, it is at rest in a stable pit, but elsewhere on the landscape, there could exist an even deeper valley. If a rare fluctuation provided enough energy to push the ball over the hill, it would roll down into the deeper valley, reaching a new state of lower potential energy. In vacuum terms, this would be a transition from a metastable vacuum to a more stable one. If our universe's vacuum were metastable, such a transition could in principle occur somewhere at some time. A tiny region of the new vacuum would form and then expand at nearly the speed of light, converting the old vacuum into the new as it swept outward. The laws of physics inside that new vacuum could be different. Particle masses could change, forces could behave differently, chemistry could be altered. The structure we know, planets, stars, atoms, might not survive within that new phase. From our viewpoint, this would be a sudden, silent rewriting of the physical rules. It is important to emphasize that this scenario is speculative. We do not know whether our vacuum is truly metastable or absolutely stable. Current measurements of particle physics suggest intriguing possibilities, but not final answers. And even if metastability exists, the expected lifetime before such a decay would likely be far longer than the current age of the universe, by many orders of magnitude in everyday terms. It is not something to fear, but rather a reminder that what we call empty space may have layers of structure and potential still hidden from our present view, beyond vacuum decay and fluctuations. Some theories extend the picture of the cosmos even further to include more than one universe. The term multiverse does not refer to a single well-defined model, but to a family of ideas in which our observable universe is one region in a larger and possibly infinite structure. In some versions, the multiverse arises from a process called eternal inflation. In this picture, the very early universe underwent a period of extremely rapid expansion, driven by high-energy fields. In most regions, that inflation ended, dropping into a lower energy state and creating a bubble of more ordinary expansion. Inside each bubble, space continues to evolve more slowly, forming galaxies and structures, much like our own observable patch. But inflation may continue elsewhere, producing more bubbles, with perhaps different properties, different effective physical constants, different patterns of matter. Our universe would then be one bubble in an enormous, possibly endless sea. Other multiverse ideas arise from quantum mechanics, from string theory, from mathematical extensions of known physics. They share a common theme. The laws and constants we measure here may not be uniquely determined. They could be one realization out of many possible sets, spread across a larger reality. If that is so, then questions like why are the constants of nature just right for stars and chemistry and life might have a different flavor. Instead of being deeply fixed from first principles, they could be environmental. We might live in a region where conditions happen to permit complexity, simply because only such regions can host observers asking the question. It is difficult to test multiverse models directly because, by definition, other universes would be causally disconnected from ours. Their light, their signals would never reach us. Still, physicists search for indirect hints, subtle imprints in the cosmic microwave background. unusual signatures in gravitational waves or constraints on how inflation could have unfolded. So far, no clear evidence has emerged, but the exploration continues, not because we need an endless series of universes to feel awe, but because following equations and symmetries sometimes leads naturally to larger frameworks than we first imagined. Another deep question involves information in a universe heading toward heat death. What happens to the information encoded in its earlier states, when stars shone, when galaxies formed, when life arose and thought about the cosmos? If all structures eventually decay, if matter is dispersed and black holes evaporate, does the information that once described those structures simply vanish, or is it conserved in some subtle way? In standard quantum theory, information is not supposed to be destroyed. The evolution of a closed system is unitary, meaning that, in principle, its initial state can be recovered from its final state if you had complete knowledge, even if the details are scrambled beyond recognition. At practical scales, this principle led to an apparent tension with black holes for a long time. When matter falls into a black hole, its detailed information seems to vanish from the viewpoint of the outside universe. If the black hole later evaporates into thermal radiation, that radiation appears featureless, lacking the imprints of what fell in. This is the essence of the black hole, information paradox. Many physicists now suspect that information is in fact preserved, that the outgoing radiation, or the structure of space-time, at very small scales, somehow encodes the lost data in an extremely subtle way. Ideas like the holographic principle suggest that all of the information in a region of space could be represented on a lower dimensional boundary, like a cosmic screen. Rather than filling the volume directly in such a view, the universe behaves a bit like a hologram. The three-dimensional picture we experience is supported by deeper patterns of information on surfaces and at horizons. If information is truly conserved, then even in a universe that approaches heat death, the final state would still carry a hidden record of everything that came before, not as readable memories, not as recoverable histories for any practical observer, but as correlations encoded in the fabric of quantum fields, a kind of cosmic archive that no one can open, yet which is never completely erased. If information can be lost, then the story is different. The universe not only cools and thins, it also forgets its own detailed past, leaving only coarse features like total energy, total charge, and broad global properties. Which of these views is correct remains an open question, entangled with our incomplete understanding of quantum gravity. Amid these layers of speculation, there is a simple thread of hope and quiet wonder. Even in scenarios where heat death is the most likely fate, the universe's journey, from a hot, dense beginning to a cold, diffuse far future, is filled with structure, with emergence, with pockets of extraordinary complexity. Stars, planets, molecules, cells, brains, civilizations all arise during the long unfolding between low-entropy past and high-entropy future. Those structures are temporary but not trivial. They are the way the universe has explored its own possibilities. For a finite time, entropy gradients make it possible for complexity to form, to endure, to think, to feel, to ask questions about where all of this is heading. Even if, on the grandest scales, equilibrium awaits, the presence of awareness within the path from order to disorder is itself a remarkable feature of cosmic history. The universe is not just evolving, it is in certain regions briefly becoming aware of that evolution through living beings like you. In this sense, speculating about what comes after heat death is not only about physics, it is also about perspective. On the one hand, we accept that our moment is incredibly small compared to the lifetimes of stars or galaxies, let alone the timescales of black hole evaporation or eventual equilibrium. On the other hand, within that small span, we have the capacity to comprehend, to model, to imagine time ranges that vastly exceed our own existence. That act of understanding is itself a kind of bridge across the abyss of duration. So as you rest with these ideas, you can let go of any need to control or change the universe's deep future. You are not responsible for the fate of galaxies or vacuum states. You are simply a brief, conscious ripple inside a vast process that began long before you and will continue long after you are gone. The equations will unfold, the entropy will rise, the expansion will carry structures further apart, whether or not there are multiverses. vacuum transitions, or rare fluctuations, beyond heat death, the cosmos will follow the laws it obeys quietly, impersonally, and yet strangely, beautifully. What remains for you is the experience of knowing that you are part of this larger story. Your thoughts, your memories, your questions about entropy and cosmic fate are themselves patterns of matter and energy, exploiting the temporary gradients available here and now. In that sense, every reflection on the universe's ending is also a celebration of your brief but real presence within its middle. You can breathe slowly and let that awareness settle like starlight fading into a calm, infinite night. Imagine that somewhere, far in the future, long after your life, long after your planet, long after your star, the universe continues on its own slow course, a vast, diluted, almost silent expanse of matter and radiation, drifting, cooling, spreading toward equilibrium. From the perspective of physics, this is a natural outcome. Entropy rises, gradients fade, differences smooth out. The engines that once powered stars and galaxies shut down one by one until the cosmos is mostly calm, featureless. And still, from the perspective of feeling, it can sound intimidating or lonely to imagine such a distant, cold horizon. But you are not living there. You are here, now, in a universe that is still young by its own standards, bright, structured, full of gradients, full of possibilities, full of chances for complexity to arise and think and wonder. You are made of matter, forged in stars in nuclear furnaces that burned long before you were born. You are cooled by radiation that has traveled across space for countless years. You are shaped by gravity, by chemistry, by the same laws that guide galaxies and black holes. And yet, you are also something more particular, a local pattern of atoms and energy organized into a living system capable of asking what all of this means. In a sense, the universe has written a story of its own evolution, beginning with an early state of low entropy, high energy, and extreme density, then allowing over billions of years for structure to condense, for stars to ignite, for planets to form, for chemistry to learn how to copy itself, and eventually for life to become aware of time of change of the future that lies ahead. When you lie back and listen to these ideas, you are inhabiting a tiny interval on that timeline, a moment so brief that it barely registers on cosmic scales, and yet, from your point of view, it is everything. It is your entire life, your memories, your choices, your relationships, your questions and fears and quiet joys, all packed into a short stretch of subjective time, nestled inside a much longer cosmic arc. Thinking about the heat death of the universe can shift your perspective. It reminds you that almost nothing you worry about is truly permanent. Stars are not permanent. Galaxies are not permanent. Even the very patterns of matter and radiation that fill space will eventually change and fade. If permanence is your standard, then everything fails. But if you allow impermanence to be part of the beauty, then the story looks different. In thermodynamics, we say that useful energy is finite, that gradients are spent over time to drive processes, to move heat from hot to cold, to power engines, to build order in small places at the cost of increasing entropy. Elsewhere, life is one expression of that principle. Your body maintains its structure by consuming free energy, by exchanging matter and heat with its environment. You are a local island of low entropy. Balanced on a constant flow of higher entropy, export, you exist, because the universe is not yet in equilibrium, because there are still differences to burn through. Seen this way, your finite lifespan is not a defect. It is a direct consequence of the same physics that permits you to exist at all. The same arrow of time that carries the universe toward higher entropy is the arrow along which your memories form, along which your experiences accumulate, along which you change and grow and eventually let go. There is a quiet comfort in recognizing that you do not stand outside this process. You are not an intruder in an indifferent universe. You are one of the ways the universe behaves under its own laws, one of the patterns that emerges when matter and energy have just the right conditions to become aware of themselves for a little while. When cosmologists talk about the far future, about black dwarfs and evaporating black holes and dilute radiation filling space, they are not trying to drain meaning from the present. They are extending the same curiosity that lets us understand atoms, stars, and galaxies to the longest timescales we can reach with theory. They are drawing a long, slow curve from the past through the present, into the unimaginable, futures ahead. You happen to live on a small section of that curve where the universe is especially rich in structure. If you focus only on the end point, you may feel a sense of loss. Why build or love or learn if everything will one day fade? But physics quietly answers that this fading is precisely what makes your moment precious. The structures you inhabit are temporary, but that transience is what allows them to change, to adapt, to carry information, to host experiences. If nothing changed, if nothing decayed, there would be no story, no evolution, no history, no you. So instead, you can let the thought of heat death act not as a threat, but as a frame, a very wide frame, around the painting of your own life. Within that frame, your choices still matter to you, your relationships still shape your days, your curiosity still opens new doors. The laws of physics do not erase this, they provide the backdrop against which it unfolds. Right now, you are in a safe, local environment, on a small planet, orbiting a stable star in a galaxy that will live for billions of years. There is time for you to rest, to breathe, to let the scale of the universe wash over you, without urgency, without pressure. You do not have to solve the mystery of existence. You do not have to decide whether the very distant future is hopeful or bleak. You can simply acknowledge that it is vast, that it is governed by understandable laws, and that your mind has the extraordinary ability to imagine it while lying still in the quiet of one human evening. As you drift towards sleep, you might picture the night sky, not only as it appears to your eyes, but as a thin slice of a much larger story. The starlight you see has traveled for years or centuries or millennia to reach you, each photon a small messenger from some distant region of space and time, carrying information about what was happening long ago. When it began its journey, by the time it arrives, the star may have changed, planets may have moved, galaxies may have evolved, but the light still arrives, still touches. Your retina still shapes your thoughts. In this moment, in a similar way, the ideas you have explored about entropy, expansion, and cosmic fate are like conceptual photons launched from decades of scientific work across generations. They have traveled through textbooks, telescopes, equations, conversations, until they reach you here, now, as gentle images in your mind. They too carry a kind of light, a cognitive glow that illuminates your inner sky. Even as your body relaxes and your awareness softens, the universe may one day approach a quiet equilibrium, a state where no new work can be done, no new structures can persist. But tonight it is still full of gradients and motion and potential. It has produced you, a temporary observer, capable of turning this knowledge into calm, instead of fear, into wonder, instead of anxiety, into a slow, deep breath in the dark. You can let your thoughts grow slower. You can imagine the galaxies receding, not as a loss, but as a gentle expansion of space itself. You can imagine entropy rising, not as an enemy, but as the quiet tendency of systems to explore all their possibilities. And you can imagine your own mind as one of those possibilities, a brief configuration of atoms that contemplated time and then, peacefully, let itself dissolve into rest. For now, nothing more is required. The universe will continue to evolve on scales far beyond you and within you. Cells will repair, neurons will reorganize, dreams may drift through your sleeping brain, all of it, part of the same grand thermodynamic story. You are safe inside this moment, free to let go. Free to sleep as the cosmos carries on its long, slow, beautiful journey.